Neutron stars, city-sized titans. When we look up at the night sky, the stars appear eternal, unchanging points of light that have burned for eons and seem destined to burn forever. Yet every star has a lifespan, and for the most massive among them, that life ends in violence. The collapse of a massive star is among the most dramatic and catastrophic events in the universe, releasing energies that defy comprehension and creating objects so strange they challenge our deepest understanding of physics. From this cosmic crucible, neutron stars are born, remnants of giants that once illuminated their galaxies, but now exist as compressed, city-sized titans. To understand the collapse of massive stars, one must first understand the process that allows stars to shine. Stars are powered by nuclear fusion, the steady, almost miraculous conversion of lighter elements into heavier ones within their cores. In stars like our Sun, hydrogen atoms fuse to form helium, releasing energy in the process. This energy radiates outward as heat and light, providing both the star's glow and the pressure that counteracts gravity's relentless inward pull. For more massive stars, those 8 or more times the mass of our Sun, fusion does not stop at helium. Their cores burn hotter and hotter, successively fusing helium into carbon and oxygen, carbon into neon, neon into magnesium, and onward through a chain of elements until they reach iron. And here lies the star's doom. Iron is the cosmic dead end of fusion. Unlike lighter elements, fusing iron consumes more energy than it produces. Once, the core of a massive star fills with iron. The balancing act that has sustained it for millions of years falters. The energy flow that countered gravity halts, and with it, the star's equilibrium collapses. In mere seconds, the balance tips catastrophically. Gravity, no longer opposed by the outward push of fusion, overwhelms the star. The iron core implodes with staggering force, shrinking from a sphere thousands of kilometers across to one only tens of kilometers in diameter. Temperatures soar to billions of degrees as atomic nuclei are crushed together. Electrons are driven into protons, producing neutrons and releasing a flood of neutrinos, ghostly particles that stream outward in incomprehensible numbers. This transformation marks the birth of a neutron star, a stellar core so compressed that matter itself has been fundamentally altered. The violence of this collapse is not contained. The outer layers of the star, still massive and filled with fuel, rebound against the suddenly rigid neutron core. The result is a supernova, an explosion so luminous it can briefly outshine an entire galaxy. In this cosmic firestorm, the elements that make up planets, oceans, and life itself are hurled into interstellar space. Calcium in our bones, oxygen in our lungs, iron in our blood. All were forged in the death throes of massive stars. The collapse of a star is therefore not only an astronomical phenomenon, but a biological one. Without it, we would not exist. But what becomes of the remnant left behind? Imagine compressing a mass greater than our Sun into a sphere no wider than Manhattan Island. That is the scale of a neutron star. In this compact corpse, the familiar laws of matter are rewritten. Atoms no longer exist as discrete entities. Electrons, once orbiting nuclei, have been forced into protons to form neutrons. The result is matter as dense as the atomic nucleus, a teaspoon of which would weigh billions of tons on Earth. The collapse of massive stars does not just produce strange objects. It produces objects that defy normal human language to describe. The physics of this collapse is still only partially understood. Neutrinos, released in such vast numbers during the implosion, are believed to play a key role in driving the outer layers of the star into space. Yet the details of how a star survives those brief moments of transition between collapse and explosion remain one of the great unsolved problems in astrophysics. Computer simulations suggest that tiny instabilities, rippling through the collapsing star, may amplify into shock waves that help eject the star's envelope. Others propose that magnetic fields and rotation play crucial roles. What is clear is that without these processes, the outer layers might never escape, and neutron stars might not be born. Supernovae have been witnessed by humanity throughout history, their sudden appearances shocking ancient stargazers. Chinese astronomers recorded the brightening of the Crab Nebula in 1054 CE, which was visible even in daylight. That brilliant light came from the death of a massive star, its core collapsing into a neutron star while its outer layers blasted outward. Today, telescopes reveal the glowing filaments of gas left behind, a cosmic tombstone marking the violence of the collapse. At its heart lies the Crab Pulsar, a spinning neutron star that continues to sweep space with beams of radiation, reminding us that collapse does not always mean final silence. As our understanding deepens, we realize that not all massive stars die the same way. The exact mass of the star's core, its rotation speed and its metallicity, the proportion of elements heavier than helium, all influence the outcome. Stars at the lower end of the massive range may produce neutron stars, while even larger ones collapse directly into black holes, bypassing the neutron star phase entirely. This boundary between neutron star and black hole remains one of astrophysics' most fascinating frontiers. Are there stars that form unstable neutron stars that collapse moments later into black holes? Could there be hybrid remnants straddling the line between the two? These are questions that drive astronomers to peer deeper into the heavens. In the end, the collapse of massive stars is not just about destruction, but transformation. A star that once lived for millions of years, shining and fusing, ends in seconds. And from that violent end comes both creation and mystery. Heavy elements are scattered to seed future worlds. Neutron stars emerge as laboratories of extreme physics, where matter and energy reach conditions unattainable on Earth. Black holes, in some cases, are born from the same process, adding their own enigmas to the cosmic story. When we consider neutron stars, these city-sized titans born of collapse, we are reminded of the duality of the universe. Creation is entwined with destruction. Death paves the way for new life. And at the heart of it all, gravity, the oldest and most universal force, writes the final chapter in the life of every massive star. For scientists and dreamers alike, to study the collapse of massive stars is to glimpse the ultimate limits of matter and energy, and to trace the cosmic pathways that led from the ashes of ancient supernovae to the beating hearts of living worlds. The collapse of a massive star produces something almost impossible to grasp. An object so compact that the normal rules of matter no longer apply. A neutron star is a place where density itself becomes alien, where the familiar building blocks of atoms are crushed into a single unbroken sea of neutrons. To describe their density in words or numbers is easy. To comprehend it with human intuition is nearly impossible. These stellar remnants redefine what it means for something to be solid, and they remind us how limited our everyday experience is when compared to the realities of the cosmos. Start with a simple analogy. On Earth, the densest substances we encounter are metals, such as osmium or iridium. A cubic centimeter of osmium weighs about 22 grams, heavy enough to surprise anyone who holds it. But compared to neutron star matter, osmium is practically weightless. Imagine taking a teaspoon of neutron star material. That tiny spoonful would weigh around 1 billion tons on Earth. That is the equivalent of the mass of Mount Everest compressed into a single spoon. This is the density of a neutron star. Matter packed so tightly that atomic structure itself is obliterated. At the heart of this density is the process of electron capture. During collapse, electrons are forced into protons, creating neutrons and releasing neutrinos. What results is neutron degenerate matter, in which neutrons are squeezed shoulder to shoulder, their quantum mechanical properties preventing them from occupying the same state. This neutron degeneracy pressure is the force that holds up the star against further collapse. It is a kind of exotic scaffolding, built not of steel or stone, but of quantum rules, the Pauli exclusion principle that forbids identical fermions from occupying the same space. Were it not for this pressure, gravity would crush the remnant into a black hole. To picture the structure of a neutron star, scientists divide it into layers, each stranger than the last. At the surface, only a few centimeters thick, lies a thin crust of normal atomic nuclei. Iron and heavier elements form during the supernova. Beneath this crust is a lattice of increasingly neutron-rich nuclei, bathed in a sea of free electrons. Deeper still, nuclei dissolve entirely, and neutrons dominate. Here, the density rises above anything we can replicate in laboratories on Earth. The innermost regions, known as the core, may hold even more exotic phases of matter. Hyperons, particles containing strange quarks, or even free quark matter itself, where neutrons break down into their constituent quarks. If such quark matter exists, neutron stars would truly be windows into the most extreme states of matter ever conceived. Numbers alone do not capture the enormity of these densities. A neutron star is typically around 20 kilometers in diameter, about the size of a city, yet contains more mass than our Sun. To put that in perspective, imagine compressing the Sun, with its diameter of 1.4 million kilometers, into something small enough to fit comfortably within the ring road of a major metropolis. The gravity on such an object is so strong that if you stood on its surface, a jump of a single centimeter would accelerate you to several million kilometers per hour in less than a second. Of course, no one could ever stand there. The surface gravity is 200 billion times that of Earth. This density also bends the very fabric of space and time. According to Einstein's general theory of relativity, the mass of a neutron star warps space-time so severely that time itself slows down near its surface. From an outside perspective, a clock ticking on a neutron star would appear to run more slowly than one on Earth. Light leaving the star is redshifted, stretched to longer wavelengths by the intense gravitational field. These relativistic effects mean that neutron stars are not only dense in matter, but dense in time and light itself. For scientists, neutron stars represent natural laboratories for physics under conditions that cannot be recreated on Earth. Particle accelerators like the Large Hadron Collider can probe high energies, but they cannot achieve the crushing densities inside neutron stars. Observations of neutron star behavior, their spin rates, their thermal cooling, their collisions, provide the only windows into this frontier of physics. When two neutron stars collide, as observed in the famous GW 170817 gravitational wave event, the aftermath reveals clues about the equation of state of ultra-dense matter, a question that has long haunted nuclear physicists. The concept of density at this scale challenges not only our science, but our imagination. When we think of something dense in everyday terms, we might picture lead weights, or perhaps a tightly packed crowd. But those images break down when dealing with neutron stars. A single sugar cube of neutron star material outweighs entire mountain ranges. If a fragment of neutron star somehow appeared on Earth, it would plunge straight through the crust, boring into the core of our planet in milliseconds under its own weight. Nothing could contain it. Nothing could resist its density. This strangeness invites speculation. Some scientists wonder whether the cores of neutron stars might harbor not just neutrons, but exotic states of matter never before seen. Could there be superfluids, where neutrons flow without resistance? Could there be superconductors, where magnetic fields are trapped in strange, tangled vortices? Observational evidence suggests that neutron stars may indeed exhibit such properties, explaining phenomena such as glitches, sudden jumps in their rotation rates thought to result from interactions between the star's crust and its superfluid interior. The density of neutron stars also connects to the ultimate cosmic hierarchy. White dwarfs, the remnants of smaller stars, are supported by electron degeneracy pressure. Neutron stars, more massive and compact, rely on neutron degeneracy. Beyond them lie black holes, where not even degeneracy pressures can halt collapse. Each stage represents a deeper level of density, a tighter embrace of gravity, and a stranger transformation of matter. Neutron stars stand at the threshold, dense enough to shred matter into its fundamental components, but not so dense that even light is lost. They are the cosmic middle ground between stars and the abyss. Perhaps the greatest challenge of all is that our language and intuition fail when trying to describe these densities. We live in a world where a ton is heavy, a kilometer is far, and a mountain is tall. But in the realm of neutron stars, such scales collapse just as surely as the star itself once did. To truly imagine a neutron star is to imagine something alien, a mountain of neutrons, a city of collapsed matter, a gravitational engine compressing reality itself. For most of us, it is enough to marvel, to let awe replace understanding, at least for a moment. And yet, it is in this density that we find connection. For as strange as they are, neutron stars are part of our story. The elements hurled into space by their birth explosions seeded the nebula that became our solar system. In a way, the density of neutron stars lives on in us, in the iron of our blood and the calcium of our bones. We are children of collapse, shaped by forces that play out on scales of density and energy that humble the imagination. The discovery of pulsars in 1967 was one of the great surprises of 20th century astronomy. Jocelyn Bell Burnell, a graduate student at Cambridge, was poring over miles of radio telescope data when she noticed something peculiar. A series of signals that repeated with uncanny regularity, ticking like a metronome. These signals pulsed every 1.33 seconds, so precise that they seemed more like the product of human technology than of nature. For weeks, the signals were jokingly labeled LGM, Little Green Men. But the true explanation turned out to be far stranger and far more profound. The signals came from a rapidly spinning neutron star. The universe had revealed a new class of object, the pulsar. Pulsars are neutron stars that spin with extraordinary speed, emitting beams of radiation from their magnetic poles. As these beams sweep across Earth, they appear as rhythmic pulses of radio waves, much like the beam from a lighthouse sweeping past a distant shore. Unlike the irregular twinkle of normal stars, pulsars tick with remarkable precision. Some spin hundreds of times per second, and their pulses arrive so regularly that they rival the accuracy of atomic clocks. The origin of this spin lies in the collapse of the parent star. When a massive star's core implodes into a neutron star, the conservation of angular momentum forces the remnant to spin faster, much like a figure skater pulling in their arms. The result is a stellar corpse spinning at dizzying rates, sometimes dozens or even hundreds of revolutions per second. The fastest pulsars, known as millisecond pulsars, whirl at over 700 rotations each second, their surfaces moving at a significant fraction of the speed of light. But spin alone is not what makes pulsars unique. It is the interplay between spin and magnetic fields that creates their beams. Neutron stars inherit the magnetic fields of their progenitor stars, but collapse concentrates those fields into an unimaginably small area. What once was a stellar magnetic field becomes a magnetism millions or even trillions of times stronger than Earth's. Charged particles trapped in these fields are accelerated along the magnetic poles, emitting streams of electromagnetic radiation. If the magnetic axis is tilted relative to the spin axis, as it often is, these beams sweep through space like searchlights. When one happens to cross Earth's line of sight, we observe a pulsar. To astronomers, pulsars are more than just curiosities. They are cosmic laboratories. Their regular pulses provide a natural clock against which a variety of physical phenomena can be measured. By tracking pulsar timing, scientists can test Einstein's theory of general relativity in extreme conditions, probing how space-time bends and warps near massive objects. Binary pulsars, where two neutron stars orbit one another, have provided some of the strongest evidence for gravitational waves long before detectors like LIGO directly observed them. As these stars spiral inward, their orbital decay matches predictions of energy loss through gravitational radiation with astonishing precision. Pulsars have also been used for practical purposes. Because their pulses are so reliable, astronomers have suggested using them for spacecraft navigation. Just as sailors once used stars and lighthouses to guide their ships, future interstellar travelers might use pulsars to orient themselves in the vast sea of space. Some even envision a pulsar-based GPS for spacecraft far beyond the reach of Earth's signals. Yet not all pulsars tick so smoothly. Some exhibit glitches, sudden jumps in rotation rate that last for fractions of a second. These glitches are thought to arise from interactions between the star's rigid crust and its superfluid interior, where neutrons flow without resistance. The abrupt transfer of angular momentum from the superfluid core to the crust causes the entire star to spin slightly faster. These glitches provide rare glimpses into the hidden physics inside neutron stars, where matter behaves in ways utterly alien to our terrestrial experience. Pulsars also host some of the strangest planetary systems ever discovered. In 1992, astronomers found the first confirmed exoplanets orbiting not a sun-like star, but a pulsar, PSRB 1257+12. These pulsar planets are bathed in radiation and exist in an environment forged by stellar death. Their presence raises fascinating questions about resilience and regeneration. Were they survivors of the original star, or did they form anew from debris after the supernova? Either way, they remind us that even in the most violent corners of the universe, planetary systems can arise. The diversity of pulsars is staggering. Young pulsars, like the Crab pulsar, spin rapidly, their beams blazing across the spectrum from radio to gamma rays. Millisecond pulsars, often found in dense globular clusters, are thought to be recycled, spun up by accreting matter from a binary companion. Magnetars, technically a subclass of neutron stars, sometimes behave like pulsars too, though their magnetic fury can twist their signals into unpredictable forms. Each new pulsar discovered adds to a catalogue that now numbers in the thousands, and yet astronomers believe we have only scratched the surface of the pulsar population in our galaxy. For all their variety, the metaphor of the lighthouse remains apt. Just as lighthouses warn sailors of hidden rocks and coastlines, pulsars signal the hidden physics of the universe. Their beams, sweeping across space, are silent testimony to the violence of their birth and the strangeness of their existence. To detect a pulsar is to intercept the heartbeat of a dead star, still pulsing long after its fiery life has ended. It is hard not to be moved by the sheer improbability of it. A massive star collapses. Its core compresses into neutrons. It spins up like a skater, and magnetic fields focus its energy into beams that cross our planet at just the right angle for our radio telescopes to detect. From that chain of improbable events comes a cosmic clock, ticking faithfully across millennia. If the universe has rhythms, pulsars are its metronomes. In contemplating pulsars, we encounter a union of extremes: death and persistence, chaos and order, collapse and regularity. They are reminders that even in the aftermath of destruction, the cosmos produces beauty and structure. Pulsars are not just relics of stellar death. They are active participants in the universe's story, illuminating physics we cannot reproduce, guiding explorers yet unborn, and whispering across light years in the steady language of pulses. To stand upon the surface of a neutron star, if such a thing were possible, would be to experience gravity in its most terrifying form. The word gravity itself hardly does justice to the crushing, inexorable force at play. On Earth, we live under the gentle tug of a planet that allows mountains to rise, oceans to swell, and human beings to stand upright. On a neutron star, gravity is no longer a tug, but a cosmic vice, squeezing with such intensity that no known material could resist. Here, the very concept of standing loses meaning, and the imagination falters when trying to picture the scale of forces involved. A neutron star typically contains about 1.4 times the mass of the Sun, compressed into a sphere only 20 kilometers across. That means its surface gravity is roughly 200 billion times stronger than Earth's. To put it another way, if you were to drop an object from just 1 meter above the surface, it would hit the ground in less than a microsecond, traveling at thousands of kilometers per second. A human, of course, could never survive such conditions. The instant you approach the star's surface, you would be flattened into a smear of atoms, spread thin by the overwhelming pull of gravity. But the strangeness goes deeper than violent numbers. Extreme gravity does not merely crush matter, it bends space and time itself. General relativity tells us that the presence of mass warps space-time, and a neutron star warps it almost beyond recognition. Light emitted from the surface of a neutron star is redshifted, stretched into longer wavelengths as it struggles to escape. From an observer's perspective on Earth, the star appears dimmer and redder than it would if gravity were absent. Time itself runs slower near the surface. A second spent standing on a neutron star would correspond to perhaps several seconds passing in the wider universe. One of the consequences of such gravity is the distortion of the star's apparent shape. When astronomers look at neutron stars, they often see more than half of their surfaces at once. The gravitational field bends the paths of light rays so strongly that photons leaving the far side of the star are curved around toward us, revealing regions that would otherwise remain hidden. It is as if the star refuses to keep secrets, forcing even its hidden hemisphere into view through the warping of space-time. Surface gravity also dictates the fate of any matter that dares to approach. Neutron stars often exist in binary systems, paired with another star. If the companion ventures too close, its gas is stripped away, spiraling toward the neutron star in a stream of glowing plasma. As the matter falls, it accelerates to a significant fraction of the speed of light. By the time it slams into the neutron star's surface or magnetic field, it has converted much of its gravitational potential energy into radiation. This process produces intense X-ray emissions, making neutron stars some of the brightest objects in the X-ray sky. Entire telescopes, like NASA's Chandra X-ray Observatory, have been designed to study these cosmic furnaces. This gravitational violence also fuels phenomena known as X-ray bursts. As matter accumulates on the neutron star's surface, it forms a thin, unstable layer of hydrogen and helium. When the pressure becomes too great, nuclear fusion ignites in a runaway process, releasing more energy in seconds than the Sun produces in days. The surface gravity ensures that this explosive burning remains confined, producing brilliant flashes of X-rays visible across the galaxy. Each burst is a reminder that the neutron star's surface is a crucible where normal matter meets extraordinary gravity. And then there are tidal forces, the differential pull of gravity across distances. On Earth, tidal forces from the Moon raise ocean tides that move gently over hours. On a neutron star, tidal forces would tear apart anything that ventured close. If a spaceship, for instance, tried to approach within a few hundred kilometers, the difference in gravitational pull between its near and far sides would rip it apart long before it reached the surface. Even atoms themselves are threatened. Approaching matter can be stretched into long filaments in a process known as spaghettification, more commonly associated with black holes, but equally brutal near neutron stars. Extreme gravity also helps explain why neutron stars are spherical, despite their rapid rotation. Earth bulges slightly at the equator because its spin counteracts gravity. Neutron stars, on the other hand, spin hundreds of times faster, yet remain nearly perfect spheres. Their gravity is so overwhelming that even centrifugal force is negligible by comparison. Only the fastest millisecond pulsars show tiny distortions, and even then, their shapes are far closer to spheres than Earth's. For astronomers, measuring the effects of neutron star gravity is one of the keys to unlocking their mysteries. Observations of X-ray emissions, gravitational redshift, and light bending provide clues to the star's mass and radius. These in turn inform the equation of state, the relationship between pressure and density inside neutron stars. By studying how gravity manifests at the surface, scientists can begin to infer what lies hidden at the core, where theory alone may not suffice. To imagine living under such gravity is an exercise in futility, but it is also a reminder of the scale of cosmic diversity. On Earth, gravity shapes our lives, but rarely overwhelms them. On a neutron star, gravity is existence itself, the defining characteristic that determines how matter behaves, how light escapes, how time flows. It is not just a force, but a sculptor, carving neutron stars into the strange, relentless forms we observe from afar. And yet, despite its ferocity, neutron star gravity is not the final word. Push just a little further, compress just a bit more mass, and neutron degeneracy pressure collapses. At that point, even quantum rules fail, and gravity wins completely. The result is a black hole, the ultimate triumph of gravity over matter. Neutron stars stand as sentinels at the threshold, showing us what happens when gravity nearly conquers, but not quite. Their surface gravity is a warning of what lies beyond, a preview of the abyss. In contemplating neutron star gravity, we are reminded that the universe operates on scales far beyond human comfort. It humbles us, it terrifies us, but it also inspires awe. From thousands of light years away, we can measure its effects, trace its fingerprints, and marvel at how gravity, the same force that lets us walk and drop stones, can reach such extremes. The surface of a neutron star is a boundary where physics bends, and where our understanding stretches to breaking point. It is, in every sense, gravity at its most extreme. For all that we have learned about neutron stars, their birth in collapse, their unimaginable density, their lighthouse beams, and their crushing gravity, these objects remain among the least understood in astrophysics. They are laboratories of extreme physics, where matter, magnetism, and gravity collide at scales we cannot replicate on Earth. The quest to study neutron stars is not just about cataloging more pulsars or measuring masses. It is about probing the very limits of nature. The future of neutron star research promises discoveries that may reshape our understanding of matter, space-time, and even the fate of the universe. One of the central mysteries concerns the equation of state for neutron star matter. This is the relationship between pressure and density at the incredible extremes inside the star. On Earth, equations of state describe gases, liquids, and solids with ease. But inside a neutron star, where matter may dissolve into neutrons, hyperons, or even quarks, The correct equation is unknown. Does matter remain as neutrons throughout? Does it transition into exotic states of quark-gluon plasma? Or are entirely new particles, predicted by advanced theories, lurking there? Future observations, especially of neutron star collisions, may help settle these questions. When two neutron stars merge, their gravitational wave signals encode information about their internal stiffness, whether they resist compression strongly or yield easily. By comparing signals with models, scientists hope to decode the equation of state written into space-time itself. The next frontier is multi-messenger astronomy. For centuries, we studied the cosmos through light alone. First with our eyes, then through telescopes tuned to radio, X-ray, and gamma-ray wavelengths. Today, we can also listen to the universe through gravitational waves. The landmark detection of GW 170817 in 2017, the collision of two neutron stars, was not only heard in ripples of spacetime by LIGO and Virgo, but also seen across the electromagnetic spectrum. This event produced gravitational waves, a burst of gamma rays, and a kilonova explosion that forged heavy elements like gold and platinum. It was the first time astronomers observed the universe with both eyes and ears, and it confirmed that neutron star mergers are cosmic factories for some of the heaviest elements in the periodic table. Future detections promise even richer insights. With more sensitive detectors like LIGO's upgrades, Virgo, Kagra in Japan, and the upcoming Einstein telescope in Europe, astronomers will catch more neutron star mergers and with greater clarity. Each signal will be a data point, narrowing the possible equations of state and revealing the diversity of neutron star properties across the galaxy. In the decades ahead, gravitational wave astronomy will shift from novelty to routine, turning neutron stars into regular informants about the nature of dense matter. Meanwhile, space observatories are sharpening our electromagnetic view. NASA's neutron star interior composition explorer, NICER, mounted on the International Space Station, is mapping the X-ray emissions of pulsars with exquisite precision. By measuring tiny delays in X-ray pulses as they skim the curved space-time around neutron stars, NICER is helping scientists pin down their radii and masses. These measurements are crucial. The size of a neutron star directly reflects the compressibility of its matter, and therefore its internal structure. Already, NICER has narrowed possibilities, hinting that neutron stars may be slightly larger and stiffer than some models predicted. Another leap will come from the Square Kilometre Array, SKA, the massive radio telescope under construction in South Africa and Australia. When complete, it will be the most sensitive radio observatory ever built, capable of detecting thousands of new pulsars, including elusive millisecond pulsars scattered across the Milky Way. With such a catalogue, astronomers can build a pulsar-based gravitational wave observatory, using the galaxy itself as a detector. By tracking tiny timing shifts in pulsars spread across the sky, scientists will search for low-frequency gravitational waves from supermassive black holes, hole mergers, adding yet another role to pulsars as tools of fundamental discovery. The future also belongs to X-ray polarimetry and gamma-ray astronomy. New instruments are beginning to measure not just the brightness and timing of neutron stars' emissions, but also their polarization, the orientation of light waves. Polarization reveals the geometry of magnetic fields and the behavior of light in curved spacetime. For magnetars with their titanic magnetic fields, polarization data could confirm exotic effects predicted by quantum electrodynamics, such as vacuum birefringence, where empty space itself behaves like a crystal, splitting light into polarized components. Observing such effects would be direct evidence of quantum physics manifesting on astronomical scales. Even more tantalizing, is the possibility that neutron stars may reveal new fundamental particles. Some theories predict that axions, hypothetical lightweight particles proposed as a candidate for dark matter, could interact with the extreme magnetic fields of neutron stars, converting into photons detectable in X-rays or radio waves. If confirmed, neutron stars could become the key to solving the mystery of dark matter, one of the great unsolved problems of physics. On the human scale, neutron stars may even play a role in the distant dream of interstellar exploration. Pulsar timing offers a universal coordinate system, a cosmic GPS that future spacecraft could use to navigate the galaxy. Unlike Earth-based signals which weaken with distance, pulsars can guide travelers billions of kilometers from home. Already, NASA's Voyager spacecraft carries a pulsar map etched onto its golden record, a kind of galactic address for any who might find it. In a poetic sense, humanity has already acknowledged pulsars and neutron stars as milestones of cosmic geography. Yet perhaps the most profound promise of neutron star research lies in its potential to surprise us. Time and again, neutron stars have revealed behaviors no one expected. Glitches, magnetar flares, pulsar planets. They defy simple categorization. Each new discovery pushes us to expand our theories, to imagine states of matter and processes we had never considered. The future will almost certainly bring more of these surprises, each one a reminder that the cosmos is stranger than we can predict. As our tools sharpen, we may also uncover connections between neutron stars and other extreme objects. The line between massive neutron stars and small black holes may blur, revealing transitional states or hybrid stars. We may discover new classes of pulsars, or even confirm the existence of quark stars, bridging theory and observation. The coming decades could well rewrite our understanding of what lies at the threshold between matter and collapse. In contemplating the future of neutron star research, we are reminded of why humanity studies the cosmos at all. Neutron stars are not just remote curiosities. They are embodiments of physics pushed to its limits. They challenge us to test our theories, to refine our instruments, and to stretch our imagination. They also remind us that the universe is not a static place, but a dynamic, evolving theater of extremes. Every observation of a neutron star is a glimpse into conditions that shape the cosmos, and perhaps even into the conditions that may one day shape its end. When Jocelyn Bell Burnell first detected those rhythmic pulses in 1967, she could not have known she had opened a door onto one of the most fertile fields of astrophysics. In the half-century since, neutron stars have transformed from mysterious signals to detailed subjects of study. Yet even now, they remain partly veiled, their cores hidden, their true nature uncertain. The next half-century may lift that veil, revealing not just what neutron stars are, but what matter itself can become when pushed beyond all earthly limits. In the end, the future of neutron star research is not just about these strange objects. It is about us. It is about humanity's ability to look outward and upward, to confront the incomprehensible, and to insist on understanding. Neutron stars stand as both mysteries and mirrors. Mysteries of matter and gravity, and mirrors of our own drive to explore. As we chase their pulses and pass their waves, we are following not just the heartbeat of collapsed stars, but the heartbeat of human curiosity. Magnetars, monsters of magnetism. Every neutron star is extraordinary, but a rare few are stranger still. These are the magnetars, stellar remnants with magnetic fields so immense they defy human imagination, trillions of times stronger than Earth's, powerful enough to distort atoms, tear molecules apart, and twist space-time itself. To understand how such monsters are born, we must return once more to the cataclysmic deaths of massive stars, where collapse and explosion create the perfect storm for their formation. Like all neutron stars, magnetars begin their lives in the throes of a supernova explosion. A massive star, exhausted of its nuclear fuel, builds an iron core it can no longer support. The core collapses, protons and electrons merge into neutrons, and a compact object, only a few tens of kilometers wide, is created in a heartbeat. The outer layers rebound, exploding outward as a supernova, scattering elements into space. In most cases, this collapse produces an ordinary neutron star, or a pulsar. But under special conditions, still debated but increasingly understood, a magnetar is forged. The key lies in rotation and magnetic field amplification. When the core collapses, conservation of angular momentum spins it up, much like any neutron star. But in some stars, the spin rate is extreme. The newborn neutron star may rotate hundreds of times per second. Combined with turbulent convection in the collapsing core, this rapid rotation drives a dynamo process, amplifying the star's magnetic field to staggering levels. What was once an ordinary stellar magnetic field is transformed into a force of cosmic proportions. Within seconds, the newborn object's magnetic field can reach 10 to the power of 14 to 10 to the power of 15 Gauss. Enough to shred magnetic storage media from Earth's orbit away. Enough to overpower every magnetic field we can produce in our laboratories by a factor of a quadrillion. Astronomers believe that only a small fraction, perhaps 1 in 10 neutron stars, are born with conditions right for this dynamo amplification. The progenitor star must be not only massive, but also fast-spinning, and possibly enriched in certain elements that alter its collapse dynamics. Supernova remnants associated with magnetars show hints that these were indeed unusual stars, perhaps among the most massive in their stellar nurseries. The aftermath of a magnetar's birth is violent. As the star forms, it emits a storm of neutrinos and gravitational waves, and its magnetic fields churn and twist the surrounding plasma. In some cases, this may even shape the geometry of the supernova explosion itself. Some astronomers speculate that certain unusually bright supernovae, known as superluminous supernova, may owe their brilliance to energy injected by a newborn magnetar, spinning at thousands of revolutions per second. Its rotational energy, converted into electromagnetic radiation, could pump extra light into the expanding debris, making the explosion far brighter than usual. If true, magnetars are not only rare objects, but also hidden engines, powering some of the most spectacular fireworks in the universe. The birth of a magnetar may also have consequences for gamma-ray bursts, the brief, powerful flashes of gamma radiation that occasionally sweep across the cosmos. While some gamma-ray bursts are explained by black hole formation, others may be triggered by the collapse of massive stars into magnetars. These millisecond magnetars, born spinning at breakneck speeds with enormous magnetic fields, could channel their energy into tightly focused jets that burst outward as gamma-ray flashes, visible billions of light years away. In this way, the birth of a magnetar might announce itself not just locally, but across half the observable universe. Observationally, astronomers identify young magnetars through their unique emissions. Unlike pulsars, which shine with regular radio pulses, magnetars reveal themselves through X-rays and gamma rays. Their surfaces, twisted and stressed by their magnetic fields, crack and quake, producing bursts of high-energy radiation. In some cases, these bursts rival the energy output of an entire galaxy for fractions of a second. The first such flare, observed, came in 1979 from a magnetar in the Large Magellanic Cloud, and its gamma rays saturated detectors across Earth, briefly outshining every other cosmic source in the sky. Such events are now known as giant flares. and they remain some of the most energetic explosions ever recorded outside of supernovae and black holes. The fact that magnetars exist at all is a challenge to theory. Their creation requires extreme fine-tuning, rapid spin, turbulent motion, and precise timing during collapse. And yet, despite their rarity, the universe has managed to produce them again and again. Today, we know of a few dozen confirmed magnetars, scattered throughout the Milky Way and nearby galaxies. Each one is a reminder that nature has a knack for pushing boundaries, creating not just ordinary stars, but cosmic outliers that defy expectation. For humanity, the birth of magnetars is more than an academic curiosity. Their outbursts are so powerful that were one to occur within a few light years of Earth, it could disrupt our planet's atmosphere and endanger life. Fortunately, no magnetars lie so close. But their very existence demonstrates how fragile our world is compared to the forces that play out in the wider galaxy. Magnetars are guardians of extremes, reminders that the universe is not built to human scale, but to scales far beyond comprehension. In the end, the birth of a magnetar is the birth of paradox. It is the death of a massive star, but also the creation of a new kind of stellar corpse, unlike any other. It is the collapse of matter into density, but also the explosion of energy into brilliance. It is rare, but its effects can echo across the cosmos. And above all, it is the moment when the universe declares that even neutron stars, already bizarre, can become stranger still. If neutron stars are titans of density, then magnetars are titans of magnetism. Their defining feature is not simply their compact size or immense gravity, but their magnetic fields, the strongest known in the universe. To say they are powerful is an understatement. The magnetic field of Earth, which shields our atmosphere and guides compass needles, measures about half a Gauss at the surface. The Sun's active regions can reach a few thousand Gauss. Laboratory magnets on Earth may push into the millions. But magnetars, their fields reach 10 to the 14th power to 10 to the 15th power Gauss, 1,000,000 billion times Earth's field. These are numbers so vast, they strain our ability to comprehend, describing forces so extreme that even the laws of physics behave differently under their sway. Such fields are not mere curiosities. They fundamentally alter matter. In the vicinity of a magnetar, atoms are stretched and distorted into needle-like shapes, their electrons confined to narrow paths along magnetic lines. Chemistry itself would collapse in the presence of such magnetism. Molecules could not form, bonds could not hold. The magnetic field alone would shred ordinary matter long before gravity could touch it. Imagine dropping an iron bar near a magnetar. Instead of simply being pulled or tugged, its atomic structure would unravel, its very identity as matter transformed. Where do these monstrous fields come from? The answer lies in the collapse and rotation of the progenitor star. As the core collapses, magnetic field lines are squeezed together, strengthening the field in proportion to the decrease in radius. A star that once had a modest magnetic field suddenly finds its magnetism concentrated into a much smaller space. But in magnetars, something more occurs. A dynamo effect, driven by rapid rotation and turbulent flows in the newborn neutron star, amplifies the field by many orders of magnitude. It is as if the universe has built a gigantic electromagnetic generator, running not on copper and coils, but on plasma and quarks. These fields are so intense that they create phenomena not seen anywhere else. One of them is quantum electrodynamic vacuum polarization. Normally, the vacuum of space is empty, but under extreme magnetism, even empty space becomes strange. Virtual particles flicker into existence, altering the way light travels. In a magnetar's field, space itself becomes birefringent, splitting light into polarized components much as a crystal does. This effect, predicted by quantum physics, has been tentatively observed in magnetar emissions, making these stars natural laboratories for theories at the intersection of quantum mechanics and relativity. The sheer power of magnetar fields is also what drives their violent outbursts. As the magnetic field twists and deforms, it stresses the star's rigid crust. Eventually, the crust cracks in a starquake, releasing pent-up energy in the form of X-rays and gamma rays. These bursts can be extraordinary. In 2004, a magnetar known as SGR 1806-20 unleashed a giant flare so powerful that it briefly ionized Earth's upper atmosphere. From a distance of 50,000 light-years, the flare released more energy in 1/10 of a second than the Sun radiates in 150,000 years. Had such an event occurred within a few dozen light-years, it might have posed a threat to Earth itself. Magnetars are reminders that the universe harbors forces of terrifying scale, indifferent to human fragility. The presence of such magnetic fields also affects how magnetars evolve. While ordinary neutron stars spin down over millions of years, gradually losing their rotational energy, magnetars lose energy much faster. Their magnetic fields act as enormous brakes, emitting strong winds of particles and radiation that rob the star of its spin. As a result, magnetars tend to be young objects, only a few thousand to tens of thousands of years old. Their magnetic fury is a brief but spectacular phase, after which they may quiet into more ordinary neutron stars. Studying magnetars is challenging precisely because of their rarity and distance. Only about 30 confirmed magnetars are known in our galaxy, scattered among the remnants of supernova explosions. They are faint, except during their flares, and they emit primarily in high-energy wavelengths, like X-rays and gamma rays, which can only be observed from space. Yet with every new detection, astronomers refine their understanding of how these stars harness their magnetic energy. Missions like NASA's NICA and ESA's Integral are helping measure the polarization and timing of magnetar emissions, opening windows into the tangled magnetospheres that surround them. The magnetic fields of magnetars may also connect to some of the greatest mysteries of modern astrophysics. In recent years, astronomers have detected fast radio bursts, FRBS, powerful millisecond-long blasts of radio energy from distant galaxies. Some repeat, some appear only once, but all are astonishingly energetic. In 2020, one such burst was traced to a magnetar in the Milky Way, SGR 1935+2154, providing the first concrete link between magnetars and FRBS. While not all FRBS may come from magnetars, the discovery suggests that their magnetic tantrums can indeed produce signals detectable across billions of light-years. For theoretical physicists, magnetars provide a natural testbed for questions about the unification of forces. Their fields are strong enough to probe limits where electromagnetism and the strong nuclear force may interact in unexpected ways. Could magnetars reveal new states of matter, where protons and neutrons themselves rearrange under magnetic pressure? Could they provide clues to physics beyond the standard model? These questions ensure that magnetars remain objects of intense scrutiny, not merely as curiosities, but as keys to deeper truths about the universe. It is easy to forget, amid all the numbers and theories, just how alien these fields are compared to our daily lives. The strongest magnets we build on Earth can levitate frogs or bend electron beams. The magnets inside hospital MRI machines are a few Teslas, powerful enough to tug ferromagnetic objects across rooms. A magnetar's field would not simply attract, it would deform matter, strip electrons, and alter quantum states. Within 1,000 kilometers of a magnetar, your very molecules would be torn apart. The human mind struggles to imagine forces so extreme, but magnetars exist to remind us that nature's imagination far exceeds our own. In contemplating magnetars' magnetic might, we encounter the universe at its most extravagant. Here is magnetism not as a tool, but as a tyrant, dominating every particle and photon in its domain. These fields shape the star's life, dictate its emissions, and announce its presence across the cosmos in bursts of X-rays, gamma rays, and perhaps even radio waves from galaxies far away. They are a reminder that the familiar forces we know, gravity, electromagnetism, nuclear interactions, can manifest in ways so extreme they border on the mythical. If the defining feature of a magnetar is its magnetic field, then its most spectacular signature is the violence that field unleashes. These stars are not quiet remnants that simply cool and fade. They are restless, unstable, and prone to catastrophic outbursts. Their surfaces quake, their fields snap and reconnect, and when they do, the energy released can dwarf entire stars. These events, starquakes and gamma-ray flares, are among the most dramatic explosions in the cosmos. Brief but ferocious, and they have only strengthened magnetars' reputation as the wildest children of stellar death. The story begins with the magnetar's crust. Although neutron stars are often described as spheres of neutrons, their outermost layers form a solid crystalline crust of nuclei embedded in a sea of electrons. This crust is incredibly rigid, 1 billion times stronger than steel, yet even it cannot withstand the relentless stress imposed by the magnetic field. As the magnetar's field twists and evolves, it strains against the crust, much like tectonic forces build up pressure along Earth's fault lines. Eventually, the crust yields. A fracture rips through the outer layers, releasing energy in a violent quake. When Earth quakes, cities tremble and landscapes shift. When a magnetar quakes, the entire star resonates. Its surface shakes, magnetic lines snap, and in the process, torrents of energy are unleashed. These events are observed as soft gamma repeaters, SGRS, and anomalous X-ray pulsars, AXPS, classes of magnetars prone to emitting bursts of high-energy radiation. The bursts vary in scale. Some are modest flashes, lasting fractions of a second. Others are intermediate bursts that can last minutes. But the most extraordinary are giant flares, explosions so powerful that they rival supernova in raw energy output, compressed into a heartbeat of time. The first giant flare ever detected came on March 5, 1979, from a magnetar in the Large Magellanic Cloud. The flare saturated gamma-ray detectors around Earth, leaving astronomers stunned. It was as if a cosmic bomb had gone off in a neighboring galaxy. Since then, only a handful of giant flares have been observed, but each has confirmed the staggering potential of magnetars. The December 27, 2004, flare from SGR 1806-20, located 50,000 light-years away, remains the brightest cosmic explosion ever recorded from outside the solar system. In a fraction of a second, it released more energy than the sun emits in 150,000 years. For a brief moment, it was the most luminous object in the sky, even affecting Earth's atmosphere despite the vast gulf of space. What drives such unimaginable power? The answer lies in the coupling of magnetism and matter. When the crust fractures, magnetic field lines twisted within the star's interior can suddenly reconfigure, snapping and reconnecting, in a process not unlike solar flares on the sun, but on scales millions of times more energetic. The sudden rearrangement releases pent-up magnetic energy, launching waves of radiation and particles outward. On Earth, solar flares can disrupt satellites and power grids. A magnetar flare, if it occurred within a few light years, would bathe our planet in lethal radiation, stripping the ozone layer and sterilizing the biosphere. Thankfully, no magnetas lurk so close. These outbursts also challenge our ability to measure. Instruments designed to detect gamma rays often saturate during giant flares, overwhelmed by the intensity of the signal. What we do record reveals not only the initial blast, but also the star's ringing. After the flare, the magnetar's crust oscillates and its magnetic field vibrates, producing quasi-periodic oscillations in the X-ray tail. These vibrations are thought to be seismic modes of the star itself, the cosmic equivalent of listening to a bell after it has been struck. By studying them, astronomers hope to probe the star's interior using magnetar flares as natural seismology tools for objects tens of thousands of light-years away. Starquakes also offer tantalizing connections to other cosmic phenomena. One of the great mysteries of recent years has been fast radio bursts, FRBS, millisecond-long flashes of radio energy from distant galaxies. In 2020, for the first time, an FRB was linked to a galactic magnetar, SGR 1935 +2154, which produced a radio burst far brighter than any previously seen from a neutron star. Though weaker than extragalactic FRBS, the event confirmed that magnetar outbursts can indeed generate such signals. If magnetars are responsible for even a fraction of FRBS observed across the universe, they may be announcing their starquakes billions of light-years away, their magnetic tantrums echoing across cosmic time. But as powerful as they are, magnetar flares are also fleeting. A giant flare lasts less than a second in its initial spike, followed by minutes of afterglow. For the magnetar itself, the event is both destructive and transformative. Its rotation may slow, its field may rearrange, and its surface may bear new scars. Yet it survives, waiting for the next rupture, the next flare. Over thousands of years, repeated quakes gradually drain the magnetar of energy, eventually leaving behind a quieter neutron star. Magnetars live fast and burn violently, their youth marked by spasms of unimaginable energy. For astronomers, these events are both gifts and challenges. Each flare provides a treasure trove of data about extreme physics. How magnetic fields evolve, how matter behaves under stresses billions of times stronger than Earth's, and how energy can be unleashed with such efficiency. But their rarity means that most magnetars lie silent during human observation, their flares separated by decades or centuries. Detecting them requires constant vigilance, a global network of satellites and telescopes ready to catch the brief flash when it comes. The prospect of future discoveries is thrilling. As detectors become more sensitive and more widespread, we may one day record a nearby magnetar flare in exquisite detail, capturing not just its gamma rays, but its gravitational waves and neutrino emissions as well. Such a multi-messenger observation would be revolutionary, giving us a complete picture of the violence within. It would be like watching a stellar earthquake with every sense at once. Yet beyond the science lies the awe. Starquakes and flares remind us that the universe is not serene. It is restless, unstable, and capable of violence beyond measure. Our planet spins in a small corner of the galaxy, protected by distance and chance from these bursts of fury. But somewhere out there, at this very moment, a magnetar may be cracking, its crust splintering, its magnetic field snapping like a whip, and a blast of gamma rays racing outward across light years, carrying the news of destruction. In contemplating these events, we glimpse not just the extremes of physics, but also the fragility of existence. Starquakes are the universe's way of releasing pent-up stress, reminders that even the densest objects cannot remain still forever. Their flares are cosmic exclamation points, brief declarations of the power locked inside neutron stars. For scientists, They are data. For philosophers, they are metaphors. For all of us, they are reminders of a cosmos that is as violent as it is beautiful. Every star dies, but not every death is equal. For ordinary stars like our Sun, the ending is gentle, a slow shedding of outer layers, leaving behind a cooling white dwarf. For massive stars, the finale is violent, a supernova explosion that seeds the cosmos with heavy elements. But for the rarest, most extreme of all stellar remnants, the magnetars, death itself becomes prolonged and spectacular, a phase of violent outbursts and gradual exhaustion, a star's extended death throes. These objects live fast, burn violently, and fade quickly compared to their quieter cousins. Their lives after birth are brief, but in those cosmic instants, they alter galaxies, shape radiation environments, and push physics to its breaking point. Unlike ordinary neutron stars, which can persist for billions of years as faint pulsars, magnetars are short-lived. Their extreme magnetic fields, the very feature that defines them, also guarantee their demise. Fields of 10 to the power of 14 to 10 to the power of 15 Gauss cannot remain stable indefinitely. As they twist and evolve, they tear at the star's crust and accelerate the decay of rotational energy. Within tens of thousands of years, a blink in cosmic time, most magnetars spend their energy, quieting into ordinary neutron stars. This brevity makes them rare, but it also makes their youth unforgettable. During their short lives, they erupt in storms of radiation, each event a violent punctuation mark in their long collapse from star to ash. The death throes of a magnetar manifest in their flare cycles. We have already seen how starquakes rupture their crusts and unleash torrents of energy. But over time, these events erode the star's structure. Each quake rearranges the magnetic field, saps rotational speed, and destabilizes the outer layers. The magnetar's surface may fracture and scar, leaving behind irregular fields and hotspots. These stresses sometimes persist as persistent X-ray emission, faint glows that slowly decay between the great outbursts. In this way, the magnetar seems to smolder like a dying fire, brightening suddenly when a flare reignites its fury. This slow unraveling is not quiet. The most powerful flares can eject matter into space, forming nebulae that glow with X-rays and radio waves long after the event. Some magnetars, like Swift-J 1834.9-0846, are surrounded by such nebulae, expanding shells energized by repeated outbursts. These structures bear witness to the violence of their parent stars, the cosmic equivalent of smoke lingering after explosions. Studying these remnants allows astronomers to reconstruct the recent history of a magnetar, piecing together its last centuries of activity. Magnetars' death throes may also overlap with phenomena we see elsewhere in astrophysics. Some astronomers argue that certain superluminous supernovae, explosions far brighter than standard types, may owe their power to the birth and rapid spin-down of a magnetar. If a magnetar forms rotating at thousands of revolutions per second, its rotational energy can feed the explosion, sustaining brightness for weeks or months. In this sense, the magnetar's death is entangled with the life cycle of galaxies, its energy shaping not only its own fate, but also the visibility of its parent's destruction across billions of light years. There is also a possible connection between magnetars and gamma-ray bursts, GRBS. While many gamma-ray bursts are thought to result from black hole formation, some may arise from hyper-energetic magnetars. These newborn stars, briefly stabilized by their rapid rotation and magnetic fields, could channel energy into focused jets that appear as gamma-ray bursts to distant observers. If so, magnetars' brief lives may echo across cosmic distances, their death throws mistaken for entirely different phenomena. As magnetars approach the end of their active phase, their behavior shifts. Their rotation slows dramatically, dropping from hundreds of rotations per second to mere seconds per turn. Their magnetic fields, once dominant, begin to decay, their energy sapped by continuous radiation. This decay releases heat, keeping the star glowing in X-rays long after its spin should have cooled it. But even this glow cannot last forever. Eventually, the fields weaken, the crust stabilizes, and the magnetar enters quiet obscurity. It becomes indistinguishable from ordinary neutron stars, just another corpse among the billions littering the galaxy. Yet even in death, magnetars leave legacies. Their outbursts enrich their environments with energetic particles. Their flares may trigger star formation in nearby clouds, compressing gas and seeding new generations of stars. Their nebulae persist, glowing reminders of past violence. And their mergers, when two neutron stars collide, may forge elements like gold and platinum, scattering them into space to become part of planets, and eventually part of us. In this sense, the death throes of magnetars are not merely endings, but transformations, threads woven into the cosmic cycle of birth, death, and rebirth. For astronomers, observing these final stages is both a challenge and an opportunity. Magnetars are so rare that catching them in the act of decline is difficult. Most we observe are already fading, their flares separated by decades or centuries. But as new telescopes come online, the Square Kilometre Array, the James Webb Space Telescope, next-generation X-ray and gamma-ray observatories, our ability to monitor them continuously improves. With luck, we may one day watch a magnetar's transition in detail, from violent youth to quiet middle age, and perhaps to merger or collapse. One possibility, still speculative, is that some magnetars may collapse further into black holes. If their magnetic energy and spin are insufficient to support them, or if they accrete matter from a companion star, their mass may cross the threshold beyond neutron degeneracy. In this case, the magnetar's brief life would end in the ultimate surrender to gravity, leaving behind only the darkness of a black hole. If so, magnetars may be stepping stones on the path from stars to singularities. Their death throws the final warning before the abyss. It is tempting to see magnetars as tragic, their lives short and tumultuous, their deaths inevitable. But tragedy is a human term. In cosmic terms, magnetars are expressions of possibility, experiments run by the universe in the laboratories of massive stars. Their deaths are simply the end of one phase and the beginning of another. Their energy does not vanish, it transforms. Their matter does not disappear, it disperses. The violence of their deaths is part of the violence that built galaxies, planets, and life. The death throes of magnetars remind us of a broader truth. The universe itself is mortal, shaped by cycles of energy that flare, fade, and flare again. In every quake and burst, magnetars whisper of impermanence. In every flare that outshines a galaxy for a second, they remind us that even the most extreme lives are measured in moments. And in their quiet fading, they tell us that all things, stars, galaxies, even universes, must eventually pass. To many astronomers, magnetars are more than just exotic curiosities. They are natural laboratories, vast experiments written into the fabric of the universe, where conditions exceed anything we could ever achieve on Earth. Particle accelerators, nuclear reactors, and supercomputers can simulate and model extreme physics. But only magnetars actually embody those extremes. Their interiors, surfaces, and magnetospheres push matter, energy, and space-time into regimes where our theories teeter on the edge of the unknown. To study magnetars is to test physics at its absolute limits. At the most basic level, Magnetars are windows into the behavior of matter under extraordinary densities and pressures. In their cores, neutrons are packed so tightly that normal atomic structures vanish, creating a sea of degenerate matter. But in magnetars, magnetic fields complicate this already bizarre state, twisting particles into narrow channels along magnetic lines. Under such conditions, quantum mechanics, relativity, and nuclear physics collide, producing effects no laboratory can replicate. Do neutrons give way to hyperons, or do quarks roam free in a quark-gluon plasma? Does magnetism suppress or encourage these transitions? Every observation of a magnetar, every pulse, flare, and afterglow provides a data point in answering these questions. The magnetospheres of magnetars, the regions of space dominated by their magnetic fields, are equally important laboratories. In these tangled, unstable environments, plasma physics plays out on cosmic scales. Magnetic reconnection, the snapping and rejoining of field lines, is thought to power their bursts and flares. On Earth, magnetic reconnection fuels solar flares and auroras. In magnetars, it unleashes energies billions of times greater. By comparing the two, scientists can explore universal principles of plasma behavior, scaling up laboratory and solar physics to the galactic level. Magnetars also let us test the predictions of quantum electrodynamics, QED, in regimes beyond Earth's reach. One such prediction is vacuum birefringence, the idea that in ultra-strong magnetic fields, empty space behaves like a crystal, splitting light into polarized components. For decades, this effect remained theoretical. But observations of light from magnetars, carefully measured for polarization, have begun to hint at birefringence in action. If confirmed, it would be one of the rare instances where quantum effects of the vacuum itself are visible on astronomical scales. In magnetars, the universe reveals that even nothingness is not simple when pressed by unimaginable forces. Perhaps most intriguing is the role of magnetars in the mystery of fast radio bursts, FRBS. These millisecond-long flashes of radio waves, coming from galaxies billions of light-years away, have baffled astronomers since their discovery in 2007. Their brevity and intensity suggest a compact source with immense energy, and magnetars are prime candidates. In 2020, the connection became clearer when a galactic magnetar, SGR 1935 plus 2154, emitted both X-rays and a radio burst detectable from Earth. Though weaker than extragalactic FRBS, the event provided direct evidence that magnetars can generate such bursts. If magnetars are responsible for even a fraction of the FRBS we observe, then they are not only laboratories for exotic physics, but also beacons that allow us to probe intergalactic space. By analyzing how FRB signals are dispersed and polarized as they travel, astronomers can map the density and magnetism of the vast cosmic web between galaxies. Magnetars may also hold clues to the nature of dark matter. Some theories suggest that dark matter particles, such as axions, could interact with magnetic fields in ways that produce detectable signals. Magnetars, with the strongest magnetic fields in the universe, are ideal testing grounds for these theories. If axions exist, they might convert into photons within magnetar magnetospheres, producing unusual X-ray or radio emissions. Detecting such a signal would revolutionize physics, providing the first direct evidence of the substance that makes up most of the matter in the cosmos. In this way, magnetars could become unexpected allies in solving one of the greatest mysteries of science. Another domain where magnetars serve as laboratories is gravitational wave astronomy. While binary neutron star mergers have already been detected, isolated magnetars may also contribute signals. Starquakes, for example, may shake the star's crust violently enough to emit faint gravitational waves, Though far weaker than merger signals, such events could one day be detectable with next-generation observatories. If observed, they would allow scientists to perform asteroseismology on magnetars, probing their interiors by listening to their vibrations across space-time itself. Even their life cycles challenge our understanding. Why do some neutron stars become ordinary pulsars while others become magnetars? What role do metallicity, mass, and rotation play in determining their fates? Are magnetars truly rare, or do many neutron stars pass through a magnetar-like phase early in their lives, visible only if we happen to catch them flaring? By cataloguing more examples and observing them across multiple wavelengths, astronomers can refine models of stellar evolution and the pathways that lead to these magnetic monsters. On the human side, magnetars offer more than just data. They inspire wonder and humility. To think that a single object, no larger than a city, can unleash energy that outshines a galaxy is to confront the smallness of our world. To imagine molecules being shredded, atoms stretched, and vacuum itself bending under magnetic stress is to acknowledge how fragile our everyday reality is in the face of universal extremes. Magnetars remind us that the laws of physics are broader, stranger, and more flexible than we once believed. Looking forward, the future of magnetar research lies in multi-messenger synergy. Observatories like NICER, Chandra, and XMM Newton track their X-ray signatures. Fermi and Swift capture their gamma-ray bursts. Radio telescopes like KIME hunt for associated FRBS. Gravitational wave detectors may one day add their perspective. Together, these instruments will weave a fuller picture of magnetars, not as isolated oddities, but as nodes in a network of cosmic phenomena that includes supernova, gamma-ray bursts, fast radio bursts, and the synthesis of heavy elements. If neutron stars are already strange, magnetars are stranger still, rarer, more violent, more extreme. But they are not just endpoints of stellar evolution. They are tools, laboratories, and cosmic experiments waiting to be deciphered. By studying them, we are not merely cataloguing the zoo of celestial objects. We are asking fundamental questions about matter, energy, and the nature of the universe itself. The beauty of science lies in this very interplay. Stars that were never meant to care about us nonetheless become teachers. Their flares illuminate not only the darkness of the galaxy, but also the boundaries of human knowledge. In magnetars, we glimpse not just the death throes of stars, but the vitality of physics, alive and unfinished, still unfolding across space-time. Pulsars, the universe's clocks. In the autumn of 1967, on a field in Cambridge, England, a young graduate student named Jocelyn Bell Burnell scanned through reams of data recorded on long strips of chart paper. She was part of a team led by Anthony Hewish, working with a newly constructed radio telescope designed to study the scintillation of quasars. The instrument, a sprawling forest of wires and poles stretched across acres of ground, was not built to discover something new, but to probe known phenomena. Yet hidden in the endless squiggles of pen traces, Bell noticed something odd. A series of sharp, regular pulses of radio signals, repeating every 1.33 seconds with astonishing precision. At first, the signal seemed almost artificial. Nothing in astronomy behaved so regularly. Stars flickered, quasars varied, but nothing ticked with machine-like punctuality. The idea that the signal might come from extraterrestrial intelligence was not dismissed out of hand. For weeks, Bell and her colleagues jokingly labeled it LGM-1, short for Little Green Men, but as she examined the data more closely, Bell noticed other sources of similar signals elsewhere in the sky. Whatever these objects were, they were not alien beacons. They were something new, something profoundly strange. In February 1968, the discovery was published. The first pulsar had been detected. It marked the beginning of an entirely new chapter in astrophysics. Bell Burnell's work revealed that neutron stars, once thought to be exotic theoretical curiosities, not only existed, but were detectable from Earth. The pulses were not messages, but lighthouses of collapsed stars, beaming radiation into the void. What began as a puzzle in radio, squiggles quickly grew into one of the most important discoveries of the 20th century. The name pulsar, short for pulsating radio star, was coined soon afterward, and within months more were found. They appeared as regular radio pulses, ticking away with almost uncanny precision. The mystery deepened. What could produce such signals? Astronomers soon realized that the only possible answer was a rapidly rotating neutron star, born from the supernova deaths of massive stars. The collapse of a stellar core into a dense remnant conserved its angular momentum, spinning it up to extraordinary speeds. Combined with an off-kilter magnetic field, this rotation produced beams of electromagnetic radiation. As the star spun, the beams swept across space, like the beam of a lighthouse. If one happened to point toward Earth, it appeared as a pulse. The discovery of pulsars was not just the identification of a new type of star, it was the confirmation of a theoretical prediction. Neutron stars had been proposed in the 1930s by Walter Baade and Fritz Zwicky, but until 1967 they remained speculative. With the first pulsar detection, the theory leapt into reality. The universe had revealed a new class of objects, compact corpses of stars ticking like cosmic clocks. The early years of pulsar research were marked by both excitement and rapid progress. Soon after Bell Burnell's discovery, astronomers found pulsars at the centers of known supernova remnants. In 1968, a pulsar was detected in the Crab Nebula, the expanding remains of a star whose explosion had been recorded by Chinese astronomers in 1054 CE. The Crab pulsar, spinning 30 times per second, provided a direct link between supernovae and neutron stars. What had once been seen as a mysterious guest star in the night sky was now understood as the fiery birth of a pulsar, still flashing nearly a millennium later. The regularity of pulsar signals quickly attracted attention from physicists. These objects were so stable that they could rival the accuracy of atomic clocks. Tiny deviations in their pulse arrival times provided a window into extreme astrophysical processes. Gravitational interactions with companions, irregularities in their crusts, and even the warping of space-time itself. Pulsars had gone from odd radio curiosities to precise cosmic instruments, capable of testing Einstein's theories in regimes far beyond Earth's laboratories. The discovery also sparked unexpected human drama. Although Anthony Hewish received the Nobel Prize in Physics in 1974 for the discovery, Jocelyn Bell Burnell was not included, despite her central role. The omission has since been widely criticized, and Bell Burnell herself has become an enduring symbol of perseverance and humility in science. She has often remarked that being left out of the Nobel freed her to pursue her research without the weight of fame. But history has remembered her contribution clearly. The first person to recognize the signal of a pulsar. Over time, the pulsar population grew. Thousands are now known across the Milky Way, some spinning every few seconds, others hundreds of times per second. These discoveries confirm that pulsars are not rare oddities, but common outcomes of stellar death. Every pulsar we see today is a lighthouse from a collapsed star, flashing across time and space, carrying information about its density, rotation, and magnetic field. The initial wonder that pulsars might be alien beacons while false was not misplaced. For in a way, pulsars do send messages. Not intentional ones, but messages written in physics. Each tick is a clue about the state of matter under pressures unimaginable on Earth. Each glitch in timing is a whisper from the star's crust, cracking under strain. Each shift in frequency is a reminder of the tug of gravity from a companion, or the gradual draining of energy into space. Astronomers learn to read these signals, turning pulses into equations, and equations into insight. Today, the story of pulsar discovery stands as a testament to the interplay between curiosity and patience. Bell Burnell's careful eye, her refusal to dismiss scruff in the data, was what opened the door to neutron star astrophysics. In an age of increasingly automated instruments and computer algorithms, her discovery reminds us of the value of human persistence and attention to detail. A graduate student with miles of chart paper revealed one of the most important cosmic phenomena of the century. The discovery of pulsars was not the end of the story, but the beginning. From that first signal in 1967, pulsars have gone on to transform astronomy, cosmology, and physics. They are timekeepers of the cosmos, natural laboratories for relativity, and, perhaps one day, navigational beacons for interstellar explorers. The discovery that began with little green men has blossomed into a field that continues to illuminate the universe, pulse by pulse, tick by tick. When Jocelyn Bell Burnell first discovered pulsars, their machine-like precision immediately stood out. Unlike the chaotic flickering of quasars or the erratic variability of ordinary stars, pulsars ticked with remarkable regularity. It soon became clear that pulsars were not merely strange stars. They were clocks of the cosmos, keeping time with an accuracy rivaling and sometimes exceeding that of the finest atomic clocks on Earth. Their pulses, racing across space, arrive with such dependability that astronomers have turned them into natural laboratories for testing the very structure of space-time. The secret to pulsars' precision lies in their compactness and rotation. A neutron star, only about 20 kilometers in diameter, can spin dozens to hundreds of times per second without tearing itself apart. Their immense gravity binds them so tightly that even at these dizzying speeds, they remain stable. Unlike Earth, whose rotation gradually wobbles due to shifting winds, tides, and internal motions, pulsars rotate with an almost unchanging rhythm. The result is a beam of radio waves that sweeps across space at regular intervals, producing a pulse train that can be measured to microsecond accuracy. Early on, astronomers realized that pulsars could serve as cosmic metronomes. By carefully recording the arrival times of their pulses, researchers could detect even the smallest deviations from uniformity. Over years and decades, such monitoring has turned pulsars into tools, not only for astrophysics, but for fundamental physics. One of the most important areas of study has been Einstein's theory of general relativity, which describes how mass and energy warp space-time. Pulsars provide an environment where relativity can be tested under conditions vastly more extreme than those on Earth. The breakthrough came in 1974, when Russell Hulse and Joseph Taylor discovered the first binary pulsar, PSRB, 1913 plus 16. Here was a pulsar orbiting another neutron star, locked in a tight orbital dance. By monitoring the timing of its pulses, astronomers could track the orbit with exquisite precision. What they found was revolutionary. The orbit was gradually shrinking, just as Einstein's equations predicted, due to the emission of gravitational waves. Decades before LIGO ever detected those waves directly, pulsars had already confirmed their existence. For this achievement, Hulse and Taylor received the Nobel Prize in Physics in 1993. Binary pulsars continue to be some of the most valuable natural experiments in physics. The so-called double pulsar system, PSRJ 0737-3039, discovered in 2003, contains two pulsars orbiting one another every 2.4 hours. Their interactions allow astronomers to measure relativistic effects with unprecedented precision: gravitational redshift, time dilation, orbital decay, and the way light bends in their intense fields. Each of these effects matches general relativity's predictions to extraordinary accuracy. Yet scientists remain eager to push further, because if any deviation were found, it could hint at physics beyond Einstein. Pulsars are not limited to testing relativity through orbits. Their precise timing also makes them sensitive detectors of gravitational waves passing through the galaxy. Networks of pulsars, spread across the sky and monitored simultaneously, act as a vast gravitational wave observatory, known as a pulsar timing array. When a low-frequency gravitational wave, perhaps from the merger of two supermassive black holes, ripples through space-time, it slightly shifts the arrival times of pulsar signals across the sky. Detecting these tiny shifts is like watching for ripples in a cosmic pond, and recent results from collaborations such as nanograv suggest that such a background of gravitational waves has indeed been glimpsed. Pulsars, therefore, extend gravitational wave astronomy into frequency ranges inaccessible to LIGO and Virgo, offering a complementary window into the universe's dynamics. Beyond relativity, pulsars' precision allows them to probe interstellar space itself. As their pulses travel through the galaxy, they are dispersed and delayed by clouds of electrons between the stars. By measuring these delays, astronomers can map the distribution of ionized gas in the Milky Way. In effect, pulsars double as probes of the invisible medium that fills the galaxy, revealing its density and structure. In some cases, their signals are even lensed and bent by intervening plasma, creating natural experiments in optics across astronomical distances. Some pulsars, known as millisecond pulsars, are especially prized for their stability. Spinning hundreds of times per second, they act as near-perfect clocks. Many of these pulsars have been recycled by accreting matter from a companion star, which spins them up to faster and faster rates. Once spun up, they can remain remarkably steady for billions of years. Timing experiments with millisecond pulsars have measured phenomena such as planetary systems, subtle orbital precession, and even the influence of dark matter clumps passing nearby. It is no exaggeration to say that these stellar clocks have become tools of precision astrophysics, rivaling the laboratory instruments of Earth. The analogy to atomic clocks is not mere poetry. In fact, pulsars may someday serve as the backbone of interstellar navigation systems. Spacecraft venturing far from Earth could use pulsars' steady ticks to triangulate their positions, much like GPS satellites guide us on Earth. In 2017, NASA's Sextant experiment successfully demonstrated pulsar-based navigation using the NICA X-ray telescope aboard the International Space Station. By timing pulses from millisecond pulsars, the system located the ISS within 5 kilometers, a proof of concept that hints at a future where deep space probes orient themselves by the ticking of neutron stars. Yet for all their precision, pulsars are not perfectly steady. Some exhibit sudden jumps in their rotation rates, known as glitches, believed to be caused by interactions between the solid crust and the superfluid interior. Others show subtle drifts in timing due to magnetic field evolution or accretion from companions. These irregularities are not flaws. They are windows into physics, otherwise inaccessible. A glitch, for example, can tell us how neutrons behave when they flow without viscosity, a property of matter that we can only study in the heart of neutron stars. In this way, even departures from perfect timing become data of immense value. The story of pulsar timing is ultimately one of humility and wonder. That collapsed stars, born in the violence of supernovae, could become the universe's most accurate clocks is a reminder of how beauty arises from destruction. Their precision is not an accident, but a consequence of gravity, quantum mechanics, and relativity working in harmony at extremes. For scientists, pulsars are more than astrophysical objects. They are instruments of nature, ticking with cosmic patience, waiting to be read. As we continue to measure them, decade after decade, pulsars will remain central to physics. They may confirm relativity to ever greater accuracy, or perhaps reveal its limits. They may open new chapters in gravitational wave astronomy or guide spacecraft across interstellar distances. Whatever their role, pulsars are now woven into the fabric of scientific exploration. They are the universe's clocks, and in their steady pulses we hear both the heartbeat of stars long dead and the rhythm of knowledge still unfolding. Among the vast zoo of pulsars, some stand out as true marvels. The millisecond pulsars. These stellar clocks spin hundreds of times per second, their beams sweeping across Earth with almost unbelievable regularity. The fastest known spins at over 700 revolutions each second, so fast that its surface whips around at nearly a quarter the speed of light. If ordinary pulsars are impressive for their stability, millisecond pulsars are extraordinary for their sheer velocity, precision, and endurance. They are the most stable natural clocks in the universe, and their very existence tells a dramatic story of stellar cannibalism, rebirth, and survival. When neutron stars are first born in supernova, they often spin rapidly, dozens of times per second. Over thousands or millions of years, however, their rotation slows as they radiate energy away. Left alone, they would eventually fade into obscurity, their beams too weak to detect. But in certain environments, a dying neutron star can be recycled into new life. This happens in binary star systems, where the neutron star orbits alongside a companion star. As the companion ages, it swells into a red giant and begins to lose its outer layers. If the neutron star's gravity captures this material, it forms an accretion disk, spiraling inward and transferring both mass and angular momentum. Like a spinning top being whipped back into motion, the neutron star accelerates, spinning faster and faster until it reaches millisecond periods. This recycling process is not gentle. The infalling matter releases tremendous energy as it slams onto the neutron star's surface, producing X-rays detectable across the galaxy. For this reason, many spinning up neutron stars are seen as low-mass X-ray binaries, LMXBS. These systems flicker with X-ray emissions as matter transfers from the companion to the neutron star, feeding and rejuvenating it. Once the accretion slows or stops, the neutron star emerges as a stable, rapidly spinning millisecond pulsar, powered by its rotation rather than accretion. The result is a clock of astonishing stability. Millisecond pulsars emit pulses with timing so precise that they rival the most advanced atomic clocks on Earth. Some have been tracked for decades without missing a beat. Their signals so regular that even deviations of a few microseconds are detectable. For astronomers, this makes millisecond pulsars invaluable tools. They can be used to test general relativity, to search for gravitational waves, to probe the interstellar medium, and even to build a galactic navigation system for future spacecraft. One of the most fascinating aspects of millisecond pulsars is their longevity. Because they spin so fast and are powered by rotational energy, they can remain active for billions of years, much longer than ordinary pulsars. They are, in a sense, the immortals of the neutron star family, ticking away long after their slower cousins have faded. This longevity makes them ideal as cosmic laboratories, providing stable signals over timescales that match human lifespans and beyond. The fastest known millisecond pulsar, PSRJ 1748-2446 AD, spins at 716 times per second. At such a rate, its surface velocity approaches 25% of the speed of light. If it spun only a little faster, centrifugal forces might overcome gravity and tear it apart. This record holder demonstrates the extreme limits of physics, how compact an object can be, how fast it can rotate, and how close it can come to destruction while remaining intact. Every millisecond pulsar, then, is a balancing act between gravity's grip and rotational fury. Millisecond pulsars also open windows into exotic astrophysics. Some of them exhibit glitches, sudden jumps in rotation caused by rearrangements of their superfluid interiors. These glitches, though rare in millisecond pulsars, provide clues to the strange states of matter deep inside. Others reveal planetary companions, discovered through subtle shifts in pulse timing. In fact, the first confirmed exoplanets ever found, orbiting PSRB 1257+12 in 1992, were discovered around a millisecond pulsar. These pulsar planets are unlikely havens for life, bombarded by radiation. But their existence proves that planetary systems can arise in the most violent and unlikely of environments. For physicists, the ultimate promise of millisecond pulsars lies in their use as pulsar timing arrays, PTAS. By monitoring dozens of these stellar clocks spread across the sky, scientists can detect tiny distortions in space-time caused by gravitational waves. Unlike LIGO, which detects high-frequency waves from stellar mass mergers, PTAS are sensitive to low-frequency gravitational waves from supermassive black hole binaries. The recent announcement from the Nanograv collaboration in 2023 suggested that such a background of low-frequency gravitational waves may have been detected, likely produced by the mergers of enormous black holes in the distant universe. If confirmed, millisecond pulsars will have opened an entirely new window on the cosmos, one where galaxies themselves are the players, colliding and merging across billions of years. Their utility does not stop there. Millisecond pulsars are also prime candidates for interstellar navigation. Because their pulses are steady and unique, a spacecraft could theoretically triangulate its position using multiple pulsars, much as GPS receivers use satellites. NASA's 2017 Sextant experiment proved this concept using the NICER telescope on the International Space Station, demonstrating that pulsars could serve as beacons for spacecraft millions of kilometers from Earth. In the far future, explorers venturing to the stars may navigate not by the constellations, but by the steady ticks of millisecond pulsars. It is worth remembering how remarkable this is. Stars that died in cataclysmic supernovae, collapsed into neutron stars, and then devoured their companions, are reborn as the most precise clocks in existence. Their violence gives rise to precision, their destruction to stability. In millisecond pulsars, nature achieves a paradox: chaos transformed into order, death remade into endurance. The discovery and study of millisecond pulsars has reshaped our view of the cosmos. They remind us that even in the aftermath of stellar death, systems can find new balance. They teach us that time itself can be kept by objects that have endured collapse, cannibalism, and radiation storms. And they invite us to imagine futures where human technology may one day sync to their rhythm, aligning our journeys with the heartbeat of the universe itself. When pulsars were first discovered, few could have imagined that such hostile, violent objects might host planets. Pulsars are the remnants of supernovae, surrounded by radiation storms, intense magnetic fields, and deadly winds of particles. Yet in 1992, astronomers Alexander Volschan and Dale Frail made a discovery that shocked the scientific world. They detected planets orbiting the pulsar PSRB 1257+12. These were the first confirmed exoplanets ever found. Not around a sun-like star, but around a dead star, flashing radio beams. The discovery was made through pulsar timing, one of the most precise astronomical techniques. Because pulsars tick so regularly, any small disturbance in their timing can be measured with extraordinary accuracy. If a planet orbits a pulsar, the star wobbles slightly around the common center of mass. This wobble changes the arrival times of its pulses by microseconds, enough for radio telescopes to detect. In the case of PSRB 1257 plus 12, the timing variations revealed the presence of not one, but 3 planets, with masses comparable to Earth's and orbits resembling those of the inner planets of our own solar system. The idea that planets could exist around such an extreme object was astonishing. The environment of a pulsar seems utterly inhospitable, bathed in X-rays, bombarded by relativistic particles, and subjected to intense magnetic fields. Yet the planets were real, and they forced astronomers to reconsider planetary formation. These pulsar planets raised immediate questions. How did they form? Were they survivors of the original supernova, or did they arise afterward from debris? One possibility is that they are second-generation planets, formed from a disk of material left behind after the supernova, or after the pulsar consumed a companion star. In this scenario, the explosion destroyed any pre-existing planetary system, but the debris coalesced into new worlds, much like planets form around young stars. Another possibility is that they are survivors, remnants of a once normal solar system that endured the death throes of their parent star. If true, these planets would have withstood one of the most violent events in the universe, battered but not destroyed. Whatever their origin, pulsar planets are profoundly exotic. Imagine a world orbiting a pulsar. The sky would be filled not with gentle sunlight, but with the rhythmic glare of deadly radiation. A compass would be useless, overwhelmed by the pulsar's magnetic fields. The surface, if any atmosphere could exist, would be scoured by high-energy particles. Life as we know it seems impossible under such conditions, though some theorists speculate that subsurface environments, shielded by thick layers of rock or ice, could conceivably offer protection. But habitability is not the main lesson of pulsar planets. Their importance lies in the fact that planets can exist in environments once thought utterly barren, expanding our sense of what a planetary system can be. The PSR B1257 plus 12 system remains the best studied, but it is not unique. Other pulsars have shown signs of planetary companions, though fewer in number. The pulsar PSR B1620-26, for instance, has a planet in a wide orbit within the globular cluster M4. This planet, sometimes nicknamed Methuselah, is estimated to be about 12 billion years old, nearly as old as the universe itself. Its survival alongside a pulsar and a white dwarf companion suggests an extraordinary history of stellar interactions. Pulsar planets also demonstrate the power of pulsar timing as a detection method. Long before astronomers could measure the faint dips of transits or the slight tugs of radial velocities, pulsar timing revealed planets with precision unmatched even today. The ability to detect Earth-mass planets orbiting distant neutron stars was a reminder that the universe could surprise us in ways no one anticipated. It also showed that planets are not rare accidents of sun-like stars, but common outcomes in diverse environments. These discoveries also carry philosophical weight. The first confirmed worlds beyond our solar system were not warm, Earth-like havens orbiting gentle stars. They were blasted, alien rocks circling the corpses of exploded suns. This origin story for exoplanet science is a humbling reminder that nature is indifferent to human expectations. The cosmos reveals itself on its own terms, not ours. Only later did astronomers begin to find exoplanets around sun-like stars, some even in habitable zones. But pulsar planets were first, forever linking the idea of other worlds to the most extreme environments imaginable. In recent years, pulsar planets have become tools for broader science, Their timing signals help refine models of neutron star interiors, magnetic field evolution, and binary dynamics. Some even suggest they might help test theories of gravitational physics. Since the presence of planets subtly alters a pulsar's timing in measurable ways. These planets, strange as they are, add yet another layer to the already extraordinary utility of pulsars. Speculation persists about whether more pulsar planets remain to be found. Because pulsar timing requires extraordinary stability in the signal, only certain pulsars are suitable for such searches. Many magnetars or young pulsars are too erratic, their pulses distorted by noise and glitches. But stable millisecond pulsars may harbor unseen companions, waiting for patient monitoring to reveal them. If so, the catalogue of pulsar planets may grow in the decades to come, perhaps revealing systems more complex than anything yet known. In imagining pulsar planets, one cannot help but reflect on the extremes of cosmic resilience. If planets can survive or reform around stars that have exploded, then planets must be even more common than we thought. They may arise wherever physics permits, in glowing disks, in shattered debris fields, even in the aftermath of stellar death. And if planets can be that resilient, then perhaps the seeds of habitability can persist too, hiding in places we have not yet dreamed to look. Ultimately, pulsar planets are stories of survival and surprise. They tell us that planetary systems are not fragile accidents, but robust phenomena, capable of enduring or reforming even after supernovae. They tell us that our search for worlds must not be confined to the gentle and familiar, but must extend to the wild and the strange. And they remind us that in astronomy, the first answers we receive are often the most unexpected. The universe chose to show us pulsar planets first. It was as if it wanted to challenge our assumptions from the very beginning. Before we found Earth-like worlds, before we discovered gas giants orbiting close to their stars, before we dreamed of habitable exoplanets, we found planets in the most improbable of places. In doing so, pulsar planets have earned a permanent place in the story of science, not as homes for life, but as heralds of discovery, teachers of humility, and emblems of the universe's restless creativity. From the moment pulsars were discovered, their uncanny regularity suggested practical uses. At first, the idea of applying the pulses of distant neutron stars to human endeavors seemed fanciful. These were objects thousands of light years away, remnants of dead stars, beaming radiation across the cosmos. Yet in the decades since, astronomers have begun to view pulsars not only as laboratories for physics, but also as tools for exploration. In the future, pulsars may serve as the backbone of interstellar navigation, guiding spacecraft across the solar system and perhaps one day beyond, much as sailors once used the stars and lighthouses to traverse Earth's oceans. The concept rests on pulsars' defining feature: their timing precision. Unlike the irregular flashes of most astronomical objects, pulsars pulse with extraordinary stability. Millisecond pulsars, in particular, spin hundreds of times per second with such consistency that their pulses arrive with microsecond accuracy. This makes them natural clocks, cosmic beacons whose ticks are as predictable as the rising of the sun. If a spacecraft can measure the arrival times of pulses from multiple pulsars, it can triangulate its position in space, just as a GPS receiver on Earth determines location by comparing signals from satellites. This vision moved from theory to reality in 2017, when NASA conducted the Sextant, Station Explorer for X-ray timing and navigation technology, experiment aboard the International Space Station. Using the Nicaea X-ray telescope, scientists observed millisecond pulsars and used their signals to calculate the ISS's position. The result was astonishing. The system pinpointed the station's location within 5 kilometers, all using nothing but the ticks of dead stars. Though Earth-based GPS is far more accurate within our planet's orbit, Sextant proved that pulsar navigation is viable, especially for spacecraft traveling beyond the reach of GPS signals. Future missions may expand this concept into a true galactic positioning system. Spacecraft venturing to Mars, the outer planets, or even interstellar space could carry small X-ray detectors tuned to pulsars. By comparing the arrival times of pulses from 3 or more known pulsars, they could determine their position autonomously, without relying on radio contact with Earth. For robotic explorers on long-duration missions, this would be invaluable. For human crews traveling far from home, it could be life-saving. Navigation would no longer depend on Earth's constant oversight, but on the cosmos itself. The appeal of pulsar navigation extends even further. Unlike artificial satellites, which must be launched, maintained, and replaced, pulsars are eternal beacons. They have ticked steadily for millions or billions of years, and they will continue to do so long after our technologies have changed. In that sense, they provide a universal reference frame, available to any civilization capable of detecting them. Indeed, when humanity sent the Voyager spacecraft into interstellar space, the famous Golden Record included a pulsar map, a diagram showing the relative positions and pulse frequencies of nearby pulsars. For any intelligent beings who might encounter the spacecraft, the map serves as a galactic address, pointing back to Earth's location. Pulsars are not only our clocks, they are our markers in the cosmic landscape. But pulsars' role in future missions is not confined to navigation alone. They will also continue to serve as scientific instruments for exploring the universe. Pulsar timing arrays already in operation use millisecond pulsars across the sky to detect low-frequency gravitational waves from supermassive black hole binaries. As telescopes like the Square Kilometre Array, SKA, come online, these arrays will become even more sensitive, turning the galaxy into a giant observatory for space-time itself. In effect, pulsars will allow us to listen to the mergers of galaxies across billions of years. Pulsars may also help us understand the interstellar medium, the tenuous gas and plasma that fills space between stars. As pulsar signals travel through this medium, they are delayed, dispersed, and sometimes scattered. By measuring these effects, astronomers can map the density and structure of the medium, much as seismologists use earthquakes to probe Earth's interior. Future spacecraft could use pulsars to chart the interstellar environment, identifying hazards, mapping gas clouds, or even detecting dark matter clumps by their subtle gravitational influence on timing. For human imagination, pulsars carry symbolic weight as well. To navigate by pulsars is to sync ourselves with the heartbeat of dead stars, to align human journeys with cosmic rhythms. It is a poetic echo of ancient sailors steering by Polaris or Polynesian navigators, reading the rising and setting of stars. Just as those navigators extended human horizons across oceans, pulsars may one day extend them across the galaxy. The difference is scale. Earth's oceans span thousands of kilometers, but the ocean of space spans trillions. The principle, however, is the same. Trust the sky to guide you. The future may bring even more ambitious uses. Some theorists imagine using pulsars as time standards for interplanetary communication, ensuring synchronization across vast distances. Others speculate about using pulsar timing to detect gravitational anomalies, even the subtle tugs of rogue planets or unseen black holes drifting through the galaxy. In every scenario, pulsars emerge not merely as objects of study, but as tools, woven into the very infrastructure of cosmic exploration. Yet for all their promise, pulsars remind us of our limitations as well. They are not evenly distributed, and only a fraction are bright or stable enough for practical navigation. Building detectors compact and sensitive enough for spacecraft remains a technological challenge. And while pulsar-based navigation is promising, it will not replace Earth-based systems anytime soon. Instead, it will complement them, filling the gap for missions that venture beyond Earth's protective sphere. Still, the vision is powerful. Imagine a spacecraft leaving Earth, guided not by signals from home, but by the steady ticking of millisecond pulsars. Imagine an astronaut looking out at the stars, knowing that her ship's course is plotted by dead suns whose beams sweep across the galaxy. Imagine explorers hundreds of years from now, voyaging between stars, their charts marked not by constellations, but by pulsars, each one a reliable beacon in the endless night. In closing, pulsars embody a rare union of destruction and utility. Born in the deaths of massive stars, they become clocks of unparalleled precision. They test relativity, reveal gravitational waves, and probe the galaxy's invisible structures. And now, they promise to guide us into the future, turning stellar corpses into navigational lighthouses. The ticking of pulsars is more than the sound of dying stars. It is the rhythm of cosmic order, a rhythm we may one day trust with our very lives as we journey beyond Earth. Quark stars, exotic hypotheses. Neutron stars already stretch the limits of physics, compressing matter into densities where protons and electrons fuse into neutrons. Their very existence proves that gravity can overwhelm atomic structure, leaving only the quantum rules of neutron degeneracy to resist further collapse. Yet physicists have long asked a tantalizing question: what happens if even neutron degeneracy is not enough? At what point does matter, under crushing gravity, take on an even stranger form? The hypothetical answer is the quark star, an object denser than neutron stars, stranger than black holes, and balanced precariously on the edge of collapse. To understand why quark stars are proposed, we must revisit the concept of degeneracy pressure. In normal matter, atoms resist compression because electrons cannot occupy the same quantum state, the Pauli exclusion principle. This resistance is what supports white dwarfs against gravity. In neutron stars, the same principle applies to neutrons, creating neutron degeneracy pressure. For stars up to about 2 solar masses, this pressure halts collapse, allowing neutron stars to exist. But what happens when the mass is greater, or when densities reach beyond what neutrons themselves can endure? Theoretical physics suggests that under such conditions, neutrons may melt, breaking down into their constituent quarks. Quarks are the fundamental particles that compose protons and neutrons, bound together by the strong nuclear force. In the cores of neutron stars, or in stars slightly heavier, the pressure may become so great that neutrons overlap, dissolve, and release their quarks into a sea of free particles. The result is a new state of matter, quark matter. If a star is composed primarily of this exotic fluid, it becomes what we call a quark star. Unlike black holes, which allow no information to escape beyond their event horizons, quark stars would remain visible. They would be compact, perhaps even smaller than neutron stars, glowing faintly with heat or surrounded by magnetospheres. They would be balanced between two extremes, more compressed than any neutron star, but not yet collapsed into the singularity of a black hole. In this sense, quark stars are cosmic in-betweeners, existing in the narrow gap between known physics and the abyss. The properties of quark stars are still speculative, but models suggest they would be extraordinary. Their densities could exceed that of neutron stars by factors of 2 or more, compressing matter into volumes unimaginably small. The surface of a quark star, if it can even be called that, might not consist of atoms or neutrons at all, but of a strange quark gluon soup. a smooth continuum of fundamental particles. Instead of a crust of heavy nuclei, as in neutron stars, quark stars could be bare, their quark matter exposed directly to space. Some theories even suggest that quark matter could be more stable than normal nuclear matter. This idea, known as the strange matter hypothesis, proposes that a mixture of up, down, and strange quarks might be the lowest energy form of matter in the universe. If true, then neutron stars are only metastable, temporary configurations destined to collapse into quark stars once conditions are right. In this picture, quark matter is not exotic at all, but fundamental. The true ground state of baryonic matter, hidden from us only by the conditions of ordinary stars and planets. The concept of quark stars has profound implications. If they exist, they would bridge the gap between neutron stars and black holes, providing clues about the ultimate fate of collapsing matter. They would also offer direct evidence about the behavior of the strong nuclear force, which binds quarks together inside protons and neutrons. Currently, our knowledge of this force comes primarily from particle accelerators, which can recreate quark gluon plasma for fleeting instants. But in quark stars, nature may maintain such states permanently, on scales larger than entire cities. The idea also raises unsettling possibilities. If strange quark matter is truly more stable than normal matter, then even a small nugget of it, sometimes called a strange lay, could, in theory, convert ordinary matter into quark matter on contact. While this scenario is highly speculative and unlikely, it underscores the radical nature of the hypothesis. Quark stars are not just curiosities. They are objects that challenge our understanding of what matter itself really is. Evidence for quark stars remains elusive, but tantalizing hints exist. Some neutron stars appear unusually small or massive compared to standard models, suggesting that their interiors may not be composed purely of neutrons. A handful of objects, such as RxJ 1856.5-3754, have been proposed as possible quark stars due to their compactness and thermal properties, though consensus has not been reached. Observations of neutron star mergers and gravitational wave signals may provide new data, allowing astronomers to test whether quark matter lurks in the cores of the densest stars. In the end, quark stars represent one of the most fascinating what-ifs in modern astrophysics. They sit at the boundary of theory and observation, promising insights into fundamental physics if they are ever confirmed. Whether they exist as rare oddities or as common phases of stellar evolution remains unknown. What is certain is that their possibility forces us to confront the limits of matter, the nature of stability, and the ways in which the universe continues to surprise us. To imagine a quark star is to imagine an object that should not exist, yet may. It is to look beyond neutron degeneracy pressure and ask, what lies deeper? What lies beneath the neutrons themselves? In answering, we are not only probing the fate of stars, but also peeling back the layers of matter, reaching toward the foundations of the cosmos. If the existence of quark stars is already a bold idea, the notion of strange quark matter takes it a step further. It proposes that matter built from quarks is not just an exotic state that appears under extreme pressures, but may actually be the true ground state of matter. More stable than the protons and neutrons that make up our everyday world. If this hypothesis is correct, then the universe is filled with the possibility of transformation. Ordinary matter is not the final story, but a temporary arrangement, destined to collapse into something stranger and more fundamental. To understand this idea, we must revisit the building blocks of the universe. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. In the nuclei of atoms, we find only up and down quarks, bound together into protons and neutrons. The other quark flavors appear only fleetingly in high-energy particle collisions, vanishing almost immediately. But what if, under extreme pressures like those in neutron stars, quarks could rearrange into a stable mixture of up, down, and strange quarks? Such a state, strange quark matter, could, in theory, be more stable than the matter we know. The strange matter hypothesis was first proposed in the late 1970s and developed further in the 1980s. It suggests that once quarks are freed from their neutron prisons, they may naturally settle into a three-flavor soup of up, down, and strange quarks. The addition of strange quarks lowers the overall energy of the system, making it more stable than pure up and down quark matter. If correct, then any sufficiently dense collection of neutrons could decay into strange matter, producing a strange star rather than an ordinary neutron star. This idea is both elegant and unsettling. Elegant, because it provides a simple explanation for the possible existence of quark stars. Unsettling, because if strange matter is truly more stable, then in principle, even a small nugget of it, a strangelet, could catalyze the conversion of normal matter into strange matter. A strangelet drifting through space and colliding with a neutron star might trigger its wholesale transformation into a strange star. Some theorists once speculated, half in jest, half in concern, that experiments producing quark-gluon plasma on Earth might accidentally generate strangelets, though careful studies have shown the risk to be negligible. Still, the thought lingers. What if ordinary matter is not the universe's preferred form? If strange matter does exist, it could explain some of the mysteries surrounding compact stars. For example, observations of unusually small or unusually heavy neutron stars might be better explained as strange stars. Unlike neutron stars, whose cores are held up by neutron degeneracy pressure, strange stars would be self-bound by the strong force itself. This means they could exist in smaller sizes without collapsing into black holes. In theory, a strange star could be only a few kilometers across, glowing faintly in X-rays, a cosmic ember of stable quark matter. Strange matter could also be responsible for peculiar astrophysical phenomena. Some have suggested that gamma-ray bursts, short, powerful flashes of energy observed in distant galaxies, might be triggered by the sudden conversion of a neutron star into a strange star. In such a scenario, the transition releases enormous energy, shaking space-time and producing an electromagnetic flash visible across billions of light-years. Similarly, strange matter might play a role in supernova dynamics, influencing how collapsing stars release energy and form compact remnants. The search for strange matter is ongoing. Physicists have hunted for strangelets in cosmic rays, hoping that small fragments of quark matter might have been ejected from violent astrophysical events and traveled to Earth. Others have looked for them in the debris of high-energy collisions at particle accelerators, like CERN's Large Hadron Collider. So far, no definitive evidence has been found, but the absence of proof does not rule out the possibility. If strange matter is stable only at very high pressures, then strangelets might not survive in the vacuum of space, making them elusive to direct detection. Astronomers, too, are on the hunt. By measuring the masses and radii of compact stars, they hope to distinguish between neutron stars and strange stars. Neutron stars should follow a predictable mass-radius relationship dictated by neutron degeneracy, while strange stars could be denser and smaller for the same mass. Missions like NICER, studying the X-ray emissions of pulsars, aim to refine these measurements. Already some stars appear to challenge the limits of neutron star theory, hinting that quark matter might lurk inside. Whether these are strange stars or simply unusually compact neutron stars remains an open question. The philosophical implications of strange matter are profound. If true, It means that the matter that makes up our bodies, our planet and our sun, is not the ultimate ground state of the universe. Instead, we live in a metastable arrangement, shielded only by the fact that strange matter requires enormous densities to form. The possibility that the universe prefers quark matter over atoms is a reminder that what feels permanent to us may, on cosmic timescales, be only temporary. And yet, this hypothesis is also a testament to the creativity of science. It emerges not from speculation alone, but from the natural extension of known physics into extreme regimes. We know quarks exist. We know they bind into protons and neutrons. We know high pressures can alter these bonds. From there, the leap to strange matter is not reckless but reasoned. It is an acknowledgement that the universe may hold states of matter beyond those we have experienced, and that the strangest ideas sometimes prove to be the most real. In the end, the possibility of strange quark matter is more than an astrophysical curiosity. It is a frontier of physics, where the smallest particles and the largest stars intersect. Whether or not strange stars exist, the search for them forces us to refine our theories, to test our models, and to confront the limits of what we know. If they do exist, then somewhere out there are stars not made of atoms, not even of neutrons, but of quarks, raw, unbound, fundamental. And if they do not, then the very process of looking for them has already expanded our vision of what matter can be. Strange matter may remain hypothetical, but so once did black holes, neutron stars, and exoplanets. Each began as an idea, resisted, doubted, and debated, until observation confirmed their existence. Perhaps one day, astronomers will point to a star and say, "Here is proof of strange matter, a new form of reality revealed." Until then, the possibility remains, waiting in the hearts of the densest stars, whispering of worlds stranger than we can yet imagine. If neutron stars are born in supernovae, and if strange stars arise from neutron stars transforming into quark stars, then what would that transition look like? Some theorists propose it would not be silent. Instead, the conversion could unleash one of the most energetic events in the cosmos, a quark nova. Though still hypothetical, quark novae represent a bridge between nuclear physics and astrophysics, a cosmic transformation, where matter itself is rewritten, releasing energies that rival the brightest explosions in the universe. To imagine a quark nova, begin with a neutron star on the edge of stability. For a time, neutron degeneracy pressure holds gravity in check. But as matter continues to accrete from a companion star, or as the star slowly cools and contracts, its central density rises. Eventually, conditions become critical. The neutrons in the core dissolve into their constituent quarks, forming a quark gluon plasma. If the strange matter hypothesis is correct, the transition may cascade outward, sweeping through the star in a chain reaction. Within milliseconds, what was once a neutron star becomes a quark star. This transformation is not gentle. The release of binding energy as neutrons melt into quarks is immense. Calculations suggest that a quark nova could outshine an entire galaxy for brief moments, releasing up to 10 to the power of 53 ergs of energy, comparable to, or even exceeding, an ordinary supernova. Unlike supernovae, however, the trigger is not nuclear fusion running out of fuel, but the collapse of neutrons into their more fundamental components. In essence, a quark nova is not just the death of a star, but the death of a kind of matter. One of the most intriguing features of quark nova models is that they may explain superluminous supernovae, explosions hundreds of times brighter than typical supernovae. Observations of these rare events have puzzled astronomers for years. Their luminosities seem too great to be powered by radioactive decay alone. the usual mechanism behind supernova light curves. A quark nova, occurring inside or shortly after a supernova, could provide the missing energy. In this scenario, the star first explodes in a traditional supernova, creating a neutron star. Then, days or weeks later, that neutron star collapses into a quark star, producing a second explosion. The two combine, amplifying the brightness and prolonging the glow, giving rise to the spectacular events we see. This dual explosion model, supernova followed by quark nova, has been used to explain unusual light curves of certain superluminous events. For example, SN 2006 GY, one of the brightest supernovae ever observed, has been suggested as a possible quark nova candidate. Whether or not this interpretation is correct, the possibility highlights how quark matter might leave fingerprints on cosmic fireworks. Quark novae may also play a role in the synthesis of heavy elements. Supernovae and neutron star mergers are known to produce elements like gold, platinum, and uranium through rapid neutron capture, the R process. But some abundance patterns observed in stars suggest that an additional source may be needed. The extreme conditions of a quark nova, with densities, temperatures, and neutrino fluxes, unlike any other environment, could provide that missing forge. If so, the jewelry we wear and the technology we build may carry within them atoms forged, not only in supernovae, but in quark novae, explosions of matter collapsing into its most fundamental form. The detection of a quark nova would be a scientific revolution, but how might we recognize one? The key would be in the timing and signatures of light and neutrinos. A quark nova following a supernova should produce a second burst of light, delayed by days or weeks, as the neutron star converts into a quark star. It might also produce distinctive neutrino signals, reflecting the change in particle composition at the core. Gravitational waves, too, could carry the imprint of the sudden collapse, offering another avenue for detection. As our observational tools improve, with more sensitive neutrino detectors, gravitational wave observatories, and wide-field telescopes, the possibility of identifying a quark nova grows. Of course, the idea remains controversial. Some astrophysicists argue that current supernova models, combined with magnetar-powered explosions, can already explain superluminous events without invoking quark novae. Others point out that the equation of state of dense matter is still uncertain, making predictions of quark nova energetics speculative. Yet the hypothesis persists because it elegantly unites particle physics with astrophysical observation, and because it offers testable predictions. Even if quark novae are rare, catching just one would prove the existence of quark matter in stars, settling debates that have raged for decades. Beyond their astrophysical significance, quark novae provoke philosophical wonder. They remind us that the universe is not static, but layered, with matter itself capable of collapsing into deeper forms. Hydrogen fused into helium, helium into carbon, carbon into iron. Stars collapse into neutrons, and perhaps neutrons collapse into quarks. Each step reveals a new frontier, a new boundary where physics reshapes itself. If quark novae exist, they are part of this cosmic cascade, a reminder that the story of matter is not finished. Imagine witnessing one. A star explodes, bright enough to rival its host galaxy. Then, as the debris expands and fades, a second explosion erupts from within, more brilliant still. To the distant observer, the sky would flare twice, as if the star had died and then died again. But in truth, the second explosion would not be death but transformation. The unveiling of a new kind of star, smaller, denser, and stranger than anything that came before. For humanity, the concept of quark novae is a challenge to imagination. We live in a world where matter seems stable, where atoms form familiar patterns, and where the earth beneath our feet feels permanent. Yet the universe tells us otherwise. Matter can collapse, rearrange, and burst forth in violence that reshapes galaxies. Stars can die twice, and hidden in those deaths may be the answers to some of physics' deepest questions. What is the true ground state of matter? What happens when neutrons themselves break? How does the strong force behave at cosmic scales? Until we catch one in the act, quark novae remain speculative, but they are no less compelling for it. They are symbols of the unfinished nature of science, reminders that beyond every frontier lies another, stranger horizon. Just as neutron stars were once dismissed as curiosities, and black holes as mathematical oddities, so too quark novae may someday move from theory to reality. When that day comes, the universe will reveal not just another kind of explosion, but another layer of itself, deeper and stranger than before. Quark stars and quark novae may sound like the stuff of theoretical speculation, but astronomy is at its best when it tests bold hypotheses against the sky. If quark stars exist, then somewhere in our galaxy or beyond, they should leave traces, subtle deviations from what we expect of neutron stars, supernovae, or pulsars. The hunt for candidates has been underway for decades, producing tantalizing clues that keep the idea alive, even in the absence of definitive proof. One of the most straightforward strategies for identifying quark stars is to look at mass and radius measurements. Neutron stars are governed by an equation of state that relates their internal pressure to their density. This relationship predicts a limited range of possible masses and radii, typically around 1.4 solar masses packed into a sphere 10 to 14 kilometers across. If astronomers find an object that is clearly smaller or denser than this, it could point toward a quark star. One candidate that drew early attention was RXJ 1856.5-3754, a nearby X-ray source discovered in the 1990s. Observations suggested that it was unusually compact, with a radius perhaps as small as 6 kilometers, too small for standard neutron star models. For a time, RXJ 1856 was hailed as the best quark star candidate. Later refinements in distance measurements expanded its estimated radius, bringing it back into neutron star territory. But the excitement it generated illustrates how close the line between neutron stars and quark stars can be. Another approach is to examine cooling curves. Neutron stars cool in predictable ways, radiating away their thermal energy over time. If quark matter exists in their cores, the cooling should be faster, as quark matter provides additional pathways for energy loss through neutrinos. Some observed neutron stars do indeed cool more rapidly than expected, hinting at exotic cores. The Cassiopeia. A neutron star, for example, has exhibited unexpected cooling rates in X-ray observations. Whether this points to quark matter, superfluidity, or some other exotic physics remains debated, but it shows how quark matter might reveal itself through thermal fingerprints. Pulsars provide another potential line of evidence. Their timing is so precise that small deviations can signal internal processes. Some pulsars exhibit glitches, sudden jumps in rotation rate, thought to arise from the dynamics of superfluid neutrons in the crust. If quark matter lurks inside, glitches might behave differently, or entirely new timing irregularities might appear. A few pulsars have shown unexplained behaviors that could hint at deeper structures, though disentangling these from magnetic and crustal effects is difficult. Supernovae too may hold clues. As discussed in the context of quark novae, some superluminous supernovae shine far brighter than models predict. While magnetar engines can explain some cases, others remain puzzling. A delayed quark nova, following an initial supernova, could naturally account for the double peaks, or prolonged brightness of certain light curves. While no event has yet been conclusively tied to this mechanism, surveys are expanding, and astronomers are watching closely for supernovae that refuse to fit the mold. Perhaps the most promising evidence comes from the domain of gravitational waves. When two neutron stars merge, as observed in the landmark event GW170817, the gravitational wave signal carries information about the star's internal structure. If one or both stars contain quark matter, the way they deform and collapse should differ subtly from pure neutron matter. Current detectors are not sensitive enough to make this distinction with certainty, but next-generation observatories, such as the Einstein telescope and Cosmic Explorer, may provide the clarity needed. A single merger with unmistakable quark matter signatures could confirm their existence beyond doubt. Some theorists also suggest that fast radio bursts, FRBS, could be linked to quark stars. If a neutron star converts suddenly into a quark star, the release of energy might produce a brief, intense radio pulse. The discovery that at least some FRBS come from magnetars complicates the picture, but it does not rule out quark star origins for others. Given the diversity of FRBS, it is plausible that multiple mechanisms are at work, with quark transitions contributing a piece of the puzzle. Another intriguing avenue is the possibility of detecting strangelets, small fragments of quark matter, in cosmic rays. If quark stars exist, collisions or disruptions might fling strangelets into space. Detecting them near Earth would provide direct evidence of quark matter. Searches have been conducted using balloon experiments, satellite detectors, and particle accelerators. But so far, no conclusive strangelet has been identified. Still, the search continues, driven by the idea that even a single strangelet could prove the reality of quark matter. Skepticism remains high, and rightly so. Many phenomena attributed to quark stars can also be explained by more conservative physics. Cooling anomalies, glitches, and bright supernovae all have alternative models that do not require exotic matter. Yet the persistence of anomalies across multiple domains, thermal, timing, spectral, and gravitational, keeps the quark star hypothesis alive. The fact that neutron star physics is still poorly constrained at the highest densities leaves the door open. The future of the search will be shaped by technology. NASA, on the International Space Station, is already measuring pulsar sizes with unprecedented precision. The square-kilometer array will vastly expand pulsar catalogues, allowing tighter constraints on mass and radius. Gravitational wave detectors will probe neutron star mergers in detail. And deep sky surveys like LSST will catch thousands of supernovae, among them perhaps the unmistakable signature of a quark nova. Each of these tools may tip the balance from speculation to evidence. In the meantime, the candidates we have, RxJ 1856, Cassiopeia A, superluminous supernovae, unusual pulsars, serve as reminders that the universe is not fully mapped. They sit uneasily in our catalogues, not quite conforming, hinting at deeper realities. Whether they are true quark stars or not, they challenge theory and sharpen our instruments, pushing us closer to understanding. To look for quark stars is to embrace astronomy at its boldest. It is to test not only our telescopes, but our imagination. Somewhere out there may be stars smaller than cities, made not of atoms or neutrons, but of quarks. Matter stripped to its essence, glowing faintly in the dark. To find one would be to glimpse the universe peeling back another layer, showing us that beneath the familiar lies something stranger still. If quark stars exist, they are not just astrophysical curiosities. They are cosmic laboratories, forcing physics into regimes no human experiment can reproduce. In them, the universe itself performs experiments on matter, at densities trillions of times greater than anything on Earth. By contemplating quark stars, we confront questions about the fundamental nature of matter, the strong nuclear force, and the ultimate fate of collapsing stars. Their implications reach far beyond astronomy, cutting into the heart of physics itself. At the most basic level, quark stars test the limits of the strong force, one of the four fundamental interactions of nature. The strong force binds quarks into protons and neutrons into nuclei. On Earth, we study it indirectly, smashing protons together in accelerators like the Large Hadron Collider to glimpse quarks for fleeting instants. But in the core of a neutron star, and perhaps in quark stars, the strong force is stretched to its breaking point. If neutrons dissolve into a quark gluon plasma, then the star becomes a stable container for free quarks, held together not by laboratory magnets, but by gravity itself. To confirm quark stars would be to prove that the strong force allows stable states of matter far beyond the nucleus. One major implication concerns the equation of state of dense matter, the relationship between pressure, density, and temperature in extreme environments. For ordinary matter, this is well understood. For neutron star matter, it is still uncertain. For quark matter, it remains almost entirely speculative. If quark stars exist, their masses and radii would provide direct evidence about the stiffness or softness of quark matter. This, in turn, would constrain models of nuclear interactions at high densities, bridging the gap between particle physics and astrophysics. The physics of quarks, usually studied at subatomic scales, would suddenly become visible in the stars dozens of kilometers across. The strange matter hypothesis deepens the stakes. If strange quark matter is indeed the most stable form of matter, then all baryonic matter, everything made of protons and neutrons, is, in a sense, metastable. Our world would not be built on the ground state of matter, but on a temporary plateau. The stability of Earth, the Sun, and all familiar objects would depend on the absence of the extreme conditions needed to trigger conversion into strange matter. This idea is both unsettling and thrilling. Unsettling because it suggests our reality is not ultimate. Thrilling because it shows that physics has deeper layers still to uncover. Another implication is in the realm of cosmology. If strange matter is stable, then the early universe, when it was hot and dense, may have produced strange quark nuggets that still roam space today. These relics, if they exist, could contribute to the universe's dark matter. Unlike ordinary matter, they would not emit light, but their gravity would influence galaxies and clusters. Quark stars, then, may not only reshape stellar astrophysics, but also help solve the mystery of dark matter, the invisible scaffolding that holds the cosmos together. Quark stars also touch on the question of black holes. Between neutron stars and black holes lies a gray zone. If quark stars occupy that space, they help define the true boundary between stable matter and gravitational collapse. The maximum mass of a quark star, the so-called Tolman-Oppenheimer-Volkoff limit for quark matter, could clarify at what point collapse to a black hole becomes inevitable. Observing quark stars would therefore refine our understanding of black hole formation, gravitational wave events, and the population of compact objects in the galaxy. Gravitational wave astronomy promises to bring this frontier into sharper focus. When two neutron stars merge, the resulting signal depends on their internal composition. If quark matter forms during the merger, the waves may carry its signature. Detecting such imprints would not only confirm quark matter, but also provide measurements of its properties. The possibility that gravitational wave detectors could hear the presence of quark matter in distant galaxies is one of the most exciting prospects in modern physics. Philosophically, quark stars challenge our concept of permanence. For centuries, atoms were considered indivisible. Then protons and neutrons seemed ultimate. Now quarks take their place. But even quarks are bound by forces we do not fully understand. If quark stars exist, they remind us that every foundation can be broken, that the universe contains layers beneath layers, and that our knowledge is always provisional. What seems fundamental today may tomorrow be revealed as only a stepping stone to something deeper. In practical terms, the study of quark stars drives innovation in both observation and theory. Astronomers must develop instruments sensitive enough to distinguish quark stars from neutron stars, more precise timing arrays, more accurate X-ray measurements, more powerful gravitational wave detectors. Physicists must refine models of dense matter, linking quantum chromodynamics with astrophysical equations. The collaboration of these fields demonstrates the unity of science. The same quarks probed in Geneva's particle accelerators may also shape the destiny of stars halfway across the galaxy. There are also speculative implications for the distant future of humanity. If quark matter is indeed more stable than ordinary matter, could advanced civilizations one day harness it as an energy source? The conversion of normal matter to quark matter would release titanic amounts of energy, orders of magnitude greater than nuclear fusion. Such technologies remain far beyond imagination today, but quark stars remind us that the universe is filled with reservoirs of potential energy. If only we can learn their secrets. In closing, the implications of quark stars are as vast as they are profound. They touch on the nature of matter, the stability of the universe, the origin of elements, the structure of space-time, and the limits of physics itself. They stand at the intersection of astrophysics, particle physics, and cosmology, a reminder that the cosmos is not a collection of separate puzzles, but a single, interwoven tapestry. Whether quark stars exist or not, their study has already deepened science. They force us to ask better questions, to refine our models, to expand our imagination. They show us that the familiar categories, neutron star, black hole, matter, vacuum, may not be the final word. Somewhere out there, perhaps, are stars smaller than cities, glowing embers of quark matter, awaiting discovery. If found, they will not only confirm a hypothesis, but rewrite our understanding of reality. Quark stars are not just a possibility. They are an invitation to look deeper, to think stranger, to accept that the universe has not yet shown us all its cards. The implications for fundamental physics are clear, but the implications for human curiosity may be greater still. Stellar mass black holes. The universe is filled with the deaths of stars, but few deaths are as dramatic or as final as the birth of a black hole. Unlike the quiet fading of a sun-like star into a white dwarf, or the dense rebirth of a massive star as a neutron star, a black hole is the endpoint of collapse itself. It is what happens when gravity wins completely, when no force in the known universe can resist its pull. Stellar mass black holes, the remnants of stars many times larger than the Sun, are the smallest members of the black hole family, yet they represent one of nature's most profound triumphs of gravity over matter. The story begins in the heart of a massive star. For millions of years, the star burns brightly, fusing hydrogen into helium, helium into carbon, and heavier elements in succession. Each fusion reaction releases energy that pushes outward, balancing the inward pull of gravity. This balance, called hydrostatic equilibrium, is what keeps stars stable. But there is a limit. When the star's core eventually fuses iron, the process halts. Unlike lighter elements, fusing iron consumes energy rather than releasing it. The furnace that has resisted gravity for so long sputters and dies. At that moment, the star has reached its tipping point. With no outward pressure to oppose it, gravity takes control. The iron core collapses in a fraction of a second, compressing matter at nearly free-fall speeds. Temperatures soar to billions of degrees, and the outer layers of the star crash inward before rebounding in a supernova explosion. In some cases, the rebounding shock is powerful enough to hurl the star's outer layers into space, enriching the galaxy with heavy elements. What remains depends on the mass of the collapsing core. If the remnant is less than about 2 to 3 times the mass of the Sun, neutron degeneracy pressure halts the collapse, leaving behind a neutron star. But if the core is heavier still, even neutron degeneracy cannot withstand gravity's relentless crush. The star collapses past the neutron stage into a singularity, a stellar mass black hole. At this point, a black hole is defined not by what it is, but by what it does. All of the star's mass is packed into a region so small that its escape velocity exceeds the speed of light. Nothing, not light, not particles, not information, can escape once it crosses the boundary. This boundary is called the event horizon, and it marks the point of no return. The core itself shrinks to a singularity, a point of infinite density, where the laws of physics as we know them break down. Surrounding it is empty space curved so steeply that escape becomes impossible. The precise details of how this collapse unfolds remain one of astrophysics' most challenging problems. Supernova simulations show that not all collapsing stars successfully explode. In some cases, the shockwave stalls, and the star's outer layers fall back inward, directly feeding the growing black hole. These failed supernovae may collapse silently, their only signature a sudden disappearance of the star. In fact, surveys of nearby galaxies have reported massive stars vanishing without a bright explosion, possible evidence of black holes forming in near silence. The mass range of stars destined for black hole collapse is still an active area of research. Typically, stars with initial masses greater than about 20 to 25 solar masses are thought to end as black holes. But metallicity, rotation, and binarity complicate the story. Stars in low metallicity environments, like those in the early universe, lose less mass through stellar winds, allowing more of their bulk to collapse into black holes. This may explain why gravitational wave detectors like LIGO have found black holes with masses far larger than those expected from stars in our own galaxy, some exceeding 50 or 60 solar masses. Rotation adds another layer. A rapidly spinning core can funnel energy into jets, potentially altering whether the star collapses fully or partially. In extreme cases, such collapses may power long gamma-ray bursts. Colossal explosions, thought to mark the birth of black holes from massive rotating stars. These events, visible across billions of light-years, may be some of the brightest announcements of stellar collapse in the cosmos. The physics of collapse is not just about mass, but about thresholds. White dwarfs are limited by the Chandrasekhar limit, about 1.4 solar masses, above which electron degeneracy fails. Neutron stars are limited by the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses, above which neutron degeneracy fails. Beyond this, there is no known force to resist gravity. Quark matter, as we have explored, might provide a temporary reprieve, but if even strange matter cannot withstand the crush, the end is inevitable. Collapse becomes unstoppable, and the black hole is born. From the outside, the formation of a black hole is both sudden and paradoxical. To a distant observer, the collapsing star seems to freeze as it approaches the event horizon, time dilating under gravity's grip. Light escaping from the surface is redshifted, stretched into longer and longer wavelengths, until it fades into darkness. To the infiling matter itself, however, the collapse is swift. The star shrinks past its horizon in moments, vanishing from view. In this way, relativity ensures that the birth of a black hole looks different depending on where you stand. Eternal collapse to one observer, instantaneous death to another. For the galaxy, the birth of stellar mass black holes is a cycle as important as the lives of stars themselves. Black holes are not sterile endpoints. They are engines of cosmic recycling. The supernovae that accompany their formation scatter heavy elements into interstellar clouds, seeding future stars and planets. The black holes themselves become anchors in binary systems, shaping the fates of their companions, powering X-ray emissions, and in some cases, merging to shake space-time with gravitational waves. The collapse of massive stars into black holes is also a reminder of cosmic diversity. Our sun, too small to collapse, will end as a white dwarf, glowing gently for billions of years. But stars 10 or 20 times its mass die in violence, collapsing into objects so dense and dark they defy intuition. Nature builds a zoo of stellar remnants, dwarfs, neutron stars, black holes, each representing a different balance between gravity and pressure, each a different outcome of the same universal rules. In contemplating the collapse of stars into black holes, we encounter one of the universe's starkest lessons. There are limits to resistance. Matter can push back against gravity only so far. Beyond that, there is surrender. And in that surrender, something new is born. Black holes are not merely dead stars. They are the triumph of gravity, the reshaping of space-time itself into an object that is less a thing than a place, a region of no return. The deaths of massive stars are endings, yes, but they are also beginnings. For black holes, for cosmic recycling, for gravitational waves rippling across space. Every stellar mass black hole is the tomb of a star and the seed of future discoveries, waiting silently in the dark. Once a stellar mass black hole forms, it does not simply sit in silence. In many cases, it continues to shape its surroundings, feeding on the material of nearby stars and announcing its presence in spectacular ways. One of the most important contexts where this happens is the X-ray binary system, a pairing of a black hole and a companion star bound by gravity. These systems are among the brightest high-energy sources in the galaxy, revealing black holes not through direct observation, but through the violence of their appetite. The mechanics are simple in principle, but dramatic in effect. A black hole exerts a powerful gravitational pull on its companion. If the companion star overflows its Roche lobe, the region within which its material is gravitationally bound, gas streams toward the black hole. Alternatively, if the star is massive and shedding material through stellar winds, the black hole can capture some of this outflow. In either case, matter spirals inward, forming an accretion disk around the black hole. The accretion disk is where the drama unfolds. As gas falls toward the black hole, gravitational energy is converted into heat and radiation. Friction and magnetic turbulence in the disk accelerate particles, raising temperatures to millions of degrees. At such extremes, the disk glows not in visible light, but in X-rays. These X-rays, emitted from the innermost regions of the disk, become the telltale signature of a feeding black hole. No other natural process in the galaxy produces such intense, flickering X-ray light. This process makes X-ray binaries vital to astronomy. Stellar mass black holes cannot be seen directly. By definition, their event horizons emit no light. But their feeding habits betray them. By monitoring the X-ray emissions of binaries, astronomers can infer the presence of black holes, measure their masses, and study their behavior. The first compelling black hole candidate, Cygnus X1, was identified this way in the early 1970s. It remains one of the most studied X-ray binaries, with a black hole of about 15 solar masses feeding from a blue supergiant companion. Accretion disks also reveal how matter behaves under extreme gravity. The inner regions of the disk orbit at relativistic speeds, close to the black hole's event horizon. General relativity predicts how the gas should move, how time dilates, and how light is redshifted in this environment. By analyzing X-ray spectra, astronomers can measure these effects directly, turning accretion disks into laboratories for relativity. For example, broadened and skewed ion emission lines in X-ray spectra reflect the warping of spacetime near the black hole. In this way, X-ray binaries allow us to test Einstein's theories in conditions impossible to reproduce on Earth. Feeding black holes are not quiet consumers. They are also dramatic broadcasters. Many X-ray binaries launch jets of plasma along their rotational axes, ejecting material at near-light speeds. These jets, visible in radio wavelengths, resemble those from supermassive black holes in active galaxies, but on smaller scales. For this reason, they are called microquasars. Systems like GRS 1915+105 display rapid variability in both X-rays and radio, showing how matter falling inward can be redirected outward in relativistic jets. Studying microquasars gives astronomers a scaled-down version of the processes at work in quasars and active galactic nuclei, letting us watch accretion and jet formation in real time. X-ray binaries are not static. Their feeding often occurs in bursts. Some systems remain faint for years, then erupt in bright outbursts as accretion suddenly increases. These X-ray transients may be triggered by instabilities in the accretion disk, similar to avalanches releasing after a slow buildup of snow. During these bursts, the system brightens dramatically, sometimes rivaling the output of entire galaxies in X-rays. Afterward, it settles back into quiescence, waiting for the next episode. The behavior of X-ray binaries also sheds light on the spin of black holes. Unlike mass, which can be inferred from orbital dynamics, spin is harder to measure. Yet it influences everything from the structure of the accretion disk to the power of the jets. By studying how the inner edge of the accretion disk behaves, particularly through X-ray spectroscopy, astronomers can estimate black hole spin. Some stellar mass black holes spin at rates close to the maximum allowed by relativity, their event horizons dragging spacetime itself around them in a phenomenon known as frame dragging. Feeding black holes are also violent teachers of time. Their X-ray light flickers and oscillates with remarkable speed, sometimes showing quasi-periodic oscillations, QPOs, signals that may originate from matter orbiting just above the event horizon. These oscillations encode information about the black hole's mass, spin, and the nature of spacetime at the very edge of the abyss. To measure them is to listen to the heartbeat of gravity itself. The environments of X-ray binaries can also be deadly. Radiation from the accretion disk and jets can strip atmospheres from nearby objects. A black hole feeding aggressively could sterilize planets in its system, making these regions hostile to life. Yet they are also cosmic recyclers. The material stripped from companion stars may eventually be blown back into interstellar space through winds and jets, seeding new regions of star formation. Even in destruction, black holes contribute to the galaxy's ongoing cycle of birth and death. From a broader perspective, X-ray binaries demonstrate that black holes are not isolated curiosities. They are active participants in galactic ecology, shaping their neighborhoods through gravity, radiation, and outflows. Some even suggest that black hole feedback from X-ray binaries may influence the evolution of star clusters, altering how stars form and die. The echoes of a feeding black hole ripple far beyond its event horizon. For astronomers, X-ray binaries remain among the richest sources of data about stellar mass black holes. They allow us to measure fundamental properties, test relativity, observe accretion physics, and even witness jet formation. Each system is a natural laboratory, extreme yet accessible, violent yet illuminating. In the end, the spectacle of X-ray binaries is a reminder of the paradox at the heart of black holes. They are born from collapse, yet they create structures of astonishing energy. They swallow, yet they shine. They destroy, yet they recycle. By feeding on their companions, black holes reveal not only their own nature, but also the deep interplay between gravity, matter, and light. If the defining feature of a black hole is its gravity, the defining boundary is its event horizon. This is the invisible sphere that separates what can escape from what cannot. Cross this line, and there is no going back. Not light, not matter, not even information can return. For stellar mass black holes, the event horizon is only a few tens of kilometers wide, small enough to fit within a city, yet it represents one of the deepest mysteries of physics. What exactly happens at the edge of no return? And does the horizon conceal something even stranger than we imagine? From the outside, the event horizon behaves as if it were the surface of an object, but it is not a surface in any material sense. It has no texture, no atoms, no crust. It is simply a region in space-time where the escape velocity equals the speed of light. Yet this boundary gives black holes their defining character. If they had no horizons, they would be little more than exotic stars. With them, they become bottomless pits in space-time, places where our current physics meets its limits. The mystery begins with relativity's prediction of time dilation. To a distant observer, matter falling toward a black hole appears to slow down as it approaches the event horizon. Its light grows redder and dimmer, stretched by the gravitational field, until it fades entirely. In this view, nothing ever quite crosses the horizon. It freezes in place, suspended at the edge. To the infalling matter itself, however, the experience is different. It plunges inward, without hesitation, crossing the horizon in seconds, oblivious to the outside world's perception. The paradox is not an illusion. It is a consequence of space-time being warped so intensely that different observers inhabit different realities. This relativity puzzle has led to deep questions about what the horizon is. Does it merely mark a region hidden from us, or does it possess its own physics? One of the most striking discoveries of the late 20th century was that horizons have thermodynamic properties. In the 1970s, Jacob Bekenstein argued that black holes should have entropy proportional to the area of their horizons. Stephen Hawking took the idea further, showing that horizons should emit radiation due to quantum effects. The combination of these insights means that horizons are not passive edges, but active participants in physics. They can radiate, evaporate, and interact with quantum fields. The information paradox is where the mystery deepens. If black holes truly erase all information that crosses their horizons, then the fundamental principle of quantum mechanics, that information is conserved, is violated. Hawking's original calculations implied exactly that. Matter falling in would be lost forever, its details erased from the universe once the black hole evaporated. For decades, physicists wrestled with the contradiction, splitting into camps. Some believed information was indeed lost, forcing a radical rewrite of quantum mechanics. Others insisted the paradox hinted at new physics beyond our current theories. One proposed solution is that information is encoded somehow on the event horizon itself, like bits of data stored on a cosmic hard drive. This idea forms the basis of the holographic principle, which suggests that the contents of a black hole's interior may be represented entirely by data imprinted on its horizon. In this view, horizons are not blank voids, but shimmering boundaries, where the universe's information is preserved in ways we do not yet understand. The debate grew even more intense with the firewall hypothesis in 2012. Some theorists argued that if information is to be preserved, then the horizon may not be the smooth, empty place relativity predicts. Instead, infalling matter might encounter a searing wall of high-energy particles at the horizon, incinerating anything that crosses. This firewall violates Einstein's principle of equivalence, the idea that free-falling observers should not feel gravity's pull. But it may be necessary to reconcile relativity with quantum mechanics. Whether firewalls exist is still unresolved. But the controversy highlights how little we truly know about the event horizon's nature. For stellar mass black holes in particular, horizons raise additional puzzles. Unlike their supermassive cousins, whose horizons can span millions of kilometers, stellar black hole horizons are small enough that quantum effects may play a relatively larger role. Does the horizon fluctuate? Does it fuzz with quantum foam? Observations of X-ray binaries, gravitational waves, and black hole mergers may provide clues. Some theories predict echoes, faint ripples in gravitational wave signals, if horizons are not perfectly smooth. Detecting such echoes would be a revolution, showing that horizons have structure after all. Despite these theoretical debates, horizons are also practical tools in astrophysics. By definition, the horizon radius, the Schwarzschild radius, depends only on the black hole's mass. This makes stellar mass black holes relatively simple objects. Measure the mass, and you know the size of the horizon. For a 10 solar mass black hole, the event horizon is about 30 kilometers across. The simplicity is deceptive, however, because what happens at or near that boundary remains unknown. Horizons are both the simplest and the most enigmatic features in astrophysics. The Event Horizon Telescope, EHT, which captured the first images of supermassive black hole shadows, has shown us what horizons look like on cosmic scales. For stellar mass black holes, direct imaging is impossible with current technology, but their presence is inferred through light curves, X-ray emissions, and gravitational waves. Even so, the shadows of horizons, the way they bend light, the way they distort their surroundings, leave fingerprints. Stellar mass black holes in binaries reveal themselves through the sharp cutoff, in emissions where the horizon swallows light whole. Ultimately, the mystery of the event horizon is not just astrophysical but existential. Horizons force us to ask whether space-time has edges, whether information is truly indestructible, and whether our theories can be reconciled. They are the ultimate testbeds for unifying relativity and quantum mechanics. To understand horizons fully is to take a step toward the long-sought theory of quantum gravity. For now, horizons remain paradoxical. They are not surfaces, yet they behave as though they have temperature and entropy. They erase information, yet may encode it. They appear smooth, yet may hide firewalls. They seem eternal, yet Hawking radiation suggests they evaporate. Each of these contradictions is a clue, pointing toward deeper physics waiting to be uncovered. The event horizon is the simplest idea in black hole theory, the line beyond which escape is impossible. Yet it is also the most mysterious. It is the veil through which we cannot see, the edge of knowledge itself. For stellar mass black holes, that veil is small, only tens of kilometers across, but its implications are as vast as the universe. Black holes are often imagined as eternal prisons, swallowing everything and releasing nothing. For centuries, that was the essence of their definition. Once something crosses the event horizon, it is gone forever. Yet, in the 1970s, Stephen Hawking turned this picture upside down with one of the most astonishing insights in modern physics. By combining the principles of quantum mechanics with the curved spacetime of general relativity, he showed that black holes are not truly black. They radiate, they glow, and over incomprehensible timescales, they can even evaporate away. The key lies in the peculiarities of the quantum world. According to quantum field theory, the vacuum of space is not empty, but seethes with fluctuations. Pairs of virtual particles and antiparticles constantly appear and annihilate, borrowing energy from the uncertainty principle. Normally, these pairs recombine almost instantly, leaving no trace. But near the event horizon of a black hole, the story changes. If one particle of the pair falls past the horizon, while the other escapes, the escaping particle becomes real, streaming away as radiation. To conserve energy, the black hole must effectively lose a tiny bit of mass. This process, repeated endlessly, is what we now call Hawking radiation. The radiation is extraordinarily faint. For a stellar mass black hole, the temperature associated with Hawking radiation is only billionths of a degree above absolute zero, far colder than the cosmic microwave background that fills the universe. Any Hawking radiation is completely drowned out by the environment. Only for tiny black holes, far smaller than any we know from stellar collapse, would the effect be strong enough to detect directly. Yet the principle is profound. Black holes are not eternal vacuum cleaners, but slowly evaporating objects. Hawking's calculation also gave black holes properties long thought impossible. They have a temperature inversely proportional to their mass. They have entropy, proportional to the area of their event horizons. These revelations launched the field of black hole thermodynamics, uniting concepts from relativity, quantum theory, and statistical mechanics. For the first time, black holes became laboratories for the deep connections between gravity and the laws of information. But Hawking radiation also sharpened the notorious information paradox. If black holes evaporate completely, what happens to the information about the matter they consumed? If it vanishes with the black hole, quantum mechanics is violated because quantum theory demands that information is conserved. For decades, Hawking himself argued that information is indeed lost, a radical conclusion that shook physics to its core. Later in life, he conceded that information may be preserved in subtle correlations within the radiation itself, though the exact mechanism remains debated. Resolving this paradox is one of the great open questions of theoretical physics, and likely requires a complete theory of quantum gravity. For stellar mass black holes, Hawking radiation is irrelevant on practical timescales. A black hole of 10 solar masses would take about 10 to the 67th power years to evaporate, many orders of magnitude, longer than the current age of the universe. For now, they are effectively permanent. But the theory suggests that if primordial black holes formed in the early universe with much smaller masses, some might be evaporating right now. Their final stages would be dramatic, releasing bursts of high-energy particles and radiation. Searches for such explosions in the gamma-ray sky continue, though none have yet been confirmed. Even if undetectable today, Hawking radiation remains one of the most important ideas in modern science because of its conceptual implications. It tells us that horizons are not absolute barriers, but quantumly leaky. It hints that gravity, thermodynamics, and quantum theory are interwoven in ways we do not yet fully understand. And it provides perhaps the best clue to the form a future theory of quantum gravity must take. The mathematics of Hawking radiation also led to remarkable generalizations. It applies not just to black holes, but to any horizon in space-time. Observers accelerating in empty space perceive a thermal bath of particles. The Unruh effect, a cousin of Hawking radiation, Cosmological horizons, such as those in our accelerating universe, also have temperatures and entropies. Horizons everywhere, it seems, are not cold voids, but thermodynamic systems. The implications ripple outward. If black holes radiate, they must eventually disappear. This means that nothing in the universe, not even black holes, is truly eternal. Over unimaginable timescales, galaxies will fade, stars will burn out, and black holes will evaporate, leaving only radiation behind. Hawking's insight thus reshaped not only black hole physics, but also cosmology's long-term vision of the universe. In the far, dark future, evaporation may be the final act of cosmic evolution. Hawking radiation has also inspired connections to other fields. In condensed matter physics, laboratory analogues of horizons have been created. In fluids, optical fibers, and Bose-Einstein condensates, to mimic the effects of horizons and search for analog Hawking radiation. These tabletop experiments suggest that while detecting Hawking radiation from real black holes may be impossible, its principles are universal and testable in other systems. For stellar mass black holes specifically, Hawking radiation reminds us of a truth often overlooked. Their event horizons are not eternal prisons, but dynamic boundaries. Though the effect is minuscule, compared to their feeding through accretion disks or mergers, it exists, and it points to deeper layers of reality. These small, hot remnants of stars are participants in cosmic thermodynamics, their fates tied not only to gravity, but to quantum fields. Philosophically, Hawking radiation is a humbling idea. Black holes, once symbols of ultimate permanence, become temporary. The universe, once imagined as filled with eternal structures, becomes transient. Everything, stars, galaxies, even space-time structures, is part of a great cycle of transformation. In this cycle, black holes do not stand outside the rules of physics. They obey them, however strange the consequences. In the end, Hawking radiation is less about what black holes do today than about what they reveal about the unity of physics. They sit at the crossroads of relativity, quantum mechanics, and thermodynamics. They force us to ask how information, energy, and space-time interrelate. And they remind us that even the darkest corners of the universe are not exempt from the subtle whisper of quantum processes. Hawking's insight remains one of the greatest intellectual achievements of the 20th century. It took the most terrifying objects in the universe and showed that they glow, faintly but inexorably, with the light of quantum fields. In doing so, it transformed black holes from bottomless pits into laboratories for the future of physics. Stellar mass black holes, though they will outlive stars and galaxies, are not eternal after all. They are mortal. And in their mortality lies the promise of deeper understanding. For decades, stellar mass black holes were invisible enigmas. We inferred their presence from X-ray binaries, from vanished stars, from the way their gravity tugged at companions. But in 2015, humanity entered a new era. For the first time, we did not simply see or infer black holes. We heard them. The Laser Interferometer, Gravitational Wave Observatory, LIGO, recorded ripples in space-time itself, generated by the collision of two stellar mass black holes over 1 billion light-years away. That single detection confirmed Einstein's century-old prediction of gravitational waves and opened a new window on the cosmos. Gravitational waves are distortions in space-time, produced whenever massive objects accelerate. Most everyday movements, planets orbiting, humans walking, generate waves far too small to detect. But when two stellar mass black holes orbit one another in a death spiral, the effect is immense. Their orbits tighten, their speeds increase to a significant fraction of light, and the curvature of space-time shudders outward like ripples on a pond. These ripples travel unimpeded across the universe, carrying information about the mass, spin, and distance of their sources. The first detection, GW150914, revealed two black holes of about 36 and 29 solar masses, merging to form a single black hole of 62 solar masses. The missing mass, about 3 suns' worth, was converted directly into gravitational wave energy in a fraction of a second. For a brief instant, the power output of that merger exceeded the light of all the stars in the observable universe combined. Yet the waves that reached Earth stretched and squeezed space by less than 1 part in 10 to the 21st power, a minuscule vibration detected by lasers, measuring changes smaller than a proton's width. It was the most delicate measurement ever made, and it revolutionized astronomy. Since then, dozens of black hole mergers have been detected. Each one tells a story about stellar death and cosmic evolution. Some black holes are heavier than expected from normal stellar collapse, hinting at stars in low metallicity environments, or even hierarchical mergers where black holes combine more than once. Others are spinning in strange configurations, suggesting turbulent origins in dense star clusters. Each detection is like an entry in a census of invisible stars, revealing populations we could never see with light alone. Gravitational wave detections also provide a new way to measure fundamental physics. The waveform, the chirp of rising frequency and amplitude as two black holes spiral together, encodes the laws of relativity in extreme conditions. Einstein's theory predicts exactly how space-time should behave as horizons merge, and so far, the data match the predictions perfectly. Yet scientists scrutinize every signal for deviations, hoping for cracks in relativity that might reveal new physics. Black hole mergers are our best laboratories for testing general relativity in its most extreme regime. For stellar mass black holes in particular, gravitational waves are transformative because they allow us to detect black holes that are completely isolated. X-ray binaries, once the primary method of discovery, represent only a fraction of all black holes. Most stellar mass black holes drift alone or with faint companions, invisible to telescopes. But if two of them form a binary and eventually merge, their final act becomes visible to detectors like LIGO, Virgo, and CAGRA. Suddenly, the hidden population of black holes is revealed through their collisions. These detections have also illuminated black hole formation channels. Do most stellar black holes form from single stars collapsing, or from interactions in dense stellar clusters? Do binaries form early, evolve together and collapse side by side, or are they dynamically paired later in clusters? The spins and masses measured by gravitational waves provide clues. For example, aligned spins suggest stars born together, while misaligned spins suggest chaotic interactions. With each detection, the picture becomes clearer.